Here we go. So, hello, welcome to the 11th FORTH2020 Zoom meeting in July 2021. So I think it will be an interesting meeting. We have a great agenda, and we start with an introduction of some new projects, and I will hand over to Peter to guide you through the sessions.
Thank you, Ulrich, for being with us again and hosting this fantastic meeting with people from all around the world. And I have a great surprise for the beginning. We have Andrew Holmes from UK with his creation, a TTL computer without any chip without any CPU from a manufacturer. He did his own CPU. And he installed FORTH 80 years ago. So, Andrew, you can start.
Right. Can I share my screen now?
Yeah.
Can you see my screen okay?
Yeah.
Yes, yes, you can see it fine.
Okay. You might recognize the picture from my website of the Mark I FORTH computer, which, as Peter says, I built about 18 years ago, and it's built in a standard DIN rack with a 64-way backplane, using sort of standard Vero cards, the motivation originally, which wasn't achieved actually, but the sort of inspiration that got me started on this was this idea that of the Novix chip, that it could execute the FORTH primitives in a single clock cycle. And I wanted to build something that could do that, and I failed because this machine does not. It takes several clock cycles for each FORTH primitive. But that was what got me started. But the thing that sort of took over was, through the design process, coming up with something that was simple enough and modular enough that, you know, I could actually practically make it and get it working. And that, you know, the practicality issue became the overriding driver in the end. So there's the machine. It's about sort of 8 or 9 cards. I've got a block diagram here, which is also on my website, which some people might recognize. So I just scroll that up. It's got an 8-bit data bus and a 16-bit address bus, and all the registers are basically, you'll recognize them as being, you know, the standard FORTH virtual machine. You've got the W and the IP and the stacks. What you might not recognize here is this kind of op thing here, which is sort of opcode, and the micro program counter, because it's a sort of micro coded machine. Probably also I ought to mention possibly a bit of a bottleneck in the design. You'll notice that the ALU, you know, we normally think of the ALU having 3 ports, you know, 2 inputs and output, but you'll see that I've got this single connection to the data bus, which means if you want to do an add or something, you've got to load one operand, load the second operand, and then move the result out, which takes 3 cycles. And also setting the ALU function takes a 4th cycle. So it sort of reminds me of an 8-bit microprocessor, you know, like a 6502. You know, you might do clear, carry, load accumulator, add, store. It's a little bit like that. And because I've got the 8-bit data path, it's also rather similar to that, because obviously the FORTH virtual machine is 16-bit, and you know, to achieve 16-bit operations, you've got the 2 8-bit operations going on. So there's a little fragment of the microcode assembly language on the right there, just as a taste to give you an idea of what it looks like. And those I've illustrated with the three common, the micro interpreter primitives, the enter, leave, and the next there. Maybe I should point out a slightly unusual operation. At the end of next, you can see exop, which means execute op, which is where the op register gets loaded into the micro program counter. So that's what triggers the running of a microcode routine. All the sort of basic forth primitives are implemented in this microcode. So that's analogous to, say, on for instance, on a 6502 forth, the things that would be the code words on that machine, are implemented in this microcode on this machine. In this assembly language on the right here, you can see, oh, it says my internet connection's unstable. I hope you can hear me okay. You can see move.
I can hear you fine.
Great. You can see at the top, you can see move w.low, IP. So, which is a memory read using the IP register as the address, moving it into the low byte of the W register. Increments the IP, does the same with the high byte, increments the IP again. So those are 8-bit operations. But you might notice a bit further down in the enter function, it pushes IP onto the return stack, as you do, decrements the return stack pointer, and it moves the IP register into the return stack with a single instruction. Well, that's just a bit of syntactic sugar in the assembler. That move on. So I could talk about more about it, that aspect of it, but let's move on to, I've got some pictures here of the actual hardware cards. The ones on my website are rather low resolution, but I've got some bigger ones here. Here we've got the clock and the instruction decoder. You can see the construction technique that I use. There are two different wiring methods used. This was the first one with the sort of point-to-point Kaimar type wire. And you can see in the picture on the left there, you can see I use some power bus bars to try and get a good power distribution. And you can see that it's a standard DIN Eurocard type form factor. The clock is divided by 2. It's actually a 1, so the machine runs at a 1 megahertz clock rate. So it's 1 micro instruction per microsecond is the speed. Now I've got this is the microcode sequencer that executes that microcode language that we were looking at a little fragment of just now, and that EEPROM there contains all the forth primitives implemented in the microcode, and then there's a few counters and simple registers on there. So that's kind of, I guess, the CPU, or the lowest level CPU as such. Then we've got I call it here an index register. On the diagram, it was the forth registers, the W register and the IP register, that those two 16-bit registers there are two identical cards like this that implement those. And that little jumper there actually selects which of the two functions it is. So the cards literally are identical, and one of them's configured to be W and the other one's configured to be IP. And these just have increment, decrement, and read, load in functions. Basically, it can put the address onto the address bus. You can load it 8 bits at a time, upper or lower half, and you can do increment and decrement on it, and it takes you know, 10 ICs. The next one I've got here is the memory card, ROM and RAM. So this is this EEPROM here. This contains the high-level forth code, which I actually, as I said earlier, I ported the Fig Forth model using Bill Ragsdale's installation manual, and I used Microsoft MASM assembler to build it, and that's what's in that EEPROM there. The stacks, they're both on the same card here, using 6116 memories. I had forgotten this, but I can see that I appear to have used a larger socket for those chips, and I wonder whether, I don't actually remember whether it supports the 6264 memory, perhaps. I don't remember what the function of the jumpers is either. I suspect that might be what it was for. And then here, so here on this card, you've got the memories for the stacks and the stack pointers, which support increment and decrement. And then this is, oh, there's 2 more to go. The IO card is the UART for the RS-232 port. Oh, and I should mention that this and the previous one, you can see the pen wiring system that I adopted for the later construction, using the combs for the wire guides. And finally, the ALU, again using the comb wiring with the 74181 ALU chips. And because, as I mentioned earlier, because of the bottleneck of the loading and reading and writing the ALU inputs and outputs, there's quite a lot of chips on there for accessing that. And there's one more card which I don't have a picture of, which is the diode ROM, which I guess that was perhaps a small design oversight that wasn't thought about early enough in the design. There was only a 4-bit field in the instruction for the sort of ALU function, and the 74181's got more than 4 control inputs. So I needed a little ROM just to decode the 4 bits up to the full number of signals required to control the ALU. So there's one extra, and that goes that decoded control signals goes over the data bus when you set the ALU function. So finally, I can't show you the machine working because I'm not at home at the moment, and I mean there'd also be a few. It's been quite a few years actually since I've powered it up, and my current laptop doesn't even have a UART anymore. It probably could be arranged, but the best I can do is a picture of from 18 years ago of a terminal session, which is also on my website, showing it doing a VList, or should I say words. I do have a software simulator, which I could show, but I've probably gone on 15 minutes already, so maybe that's long enough.
Andrew, but, I invite you for the next meeting. We give you a slot with 15 or 20 minutes again, because this is fantastic. This is amazing work.
Well, thank you very much.
And I am so happy you are with us in the group. It's another dream come true for me as further.
Fantastic.
John, it's Peter ready. Do you want to present him then? Andrew, we'll see you on the next meeting then. You continue.
So I'm
okay.
I'm still sorting out something here because it's just gone crazy. So is anybody else ready at the moment, or?
We have after
we could move.
Phillip Eaton, or who?
Is it possible to swap the order? Because Peter's obviously a little busy. Is it possible that we could move? Philip, would you be able to present earlier?
Yeah. Well, this is the right time anyway, isn't it?
Well, exactly. So maybe if you just take your original spot, and we'll have Peter come on when he's ready. So take it away.
Okay, let me see what I can do. Okay. I have to familiarize myself with Zoom. I tried to do this earlier on, but of course, I've now forgotten what I did earlier, and now I can't find everything. Oh, great.
Well, we could talk for a little bit while you're getting ready.
I've got a PowerPoint open on my desktop and it's not showing up in Zoom. I don't know where it is. It's unbelievable.
Those guys who make a hardware presentation, it's more complicated. No, you need to have your things working, and not always they are. They will be ready for the meeting. Sometimes you have a small problem, no?
Okay, yeah. Okay, I'll just do a full screen. That's probably the easiest thing, and shift things around as necessary.
Okay.
It's just not there. How can it not be there? I tried this earlier on actually, and it was there, but it was on my own private Zoom call, and now it's not. Okay, let me just share the screen, and we'll work it out. All right.
Okay, we can see all sorts of things. Vectrex fourth slides. Yeah.
There we go. Slide 1. Hopefully you can see that.
Yep.
Right. So Vectrex fourth programming. If you were at Euro 4th 2018, some of this might be familiar because it's basically a rehash of that presentation with all the new stuff that's happened in more recently. I'm also sharing a camera image that looks very black at the moment. That will come alive a bit later on. I've also got a second share going from my mobile phone to see what this thing looks like. So yeah, it's looking pretty good at the moment. So yes, what is Vectrex? You can see a Vectrex on the left-hand side here. It's a video game console from the 1980s. I think it came out in about 1983, something like that. It was on the market for about a year and a half. Then the video game crash of the 80s happened and it was all forgotten about. So they're relatively rare these days, but they are available. You can buy them on eBay if you've got $300 or $400 kicking around. On the right-hand side, you can see my two boys playing on a Vectrex each, having a bit of fun. There you go. Very quick thing about my background. I spent the 1990s programming Z80 single board computers in Forth, and then from 2000 onwards, I moved to London and then eventually on to Zurich working on financial systems. And I haven't actually coded anything really properly for about 20 years. And in 2016, at the bottom there, I acquired a dead Vectrex and I fixed it. And then I thought, okay, what is a Vectrex? What can I do with it? So first thing, what is it? It's a single board computer, strangely enough, with a video, a vector video that's attached to it in the box. It's got a 6809 processor, 1K of RAM, 8K of ROM. It's got a cartridge slot at the bottom. It's got a 6522 VIA and a sound chip, an AY38912, as you can see there. It's pretty basic, couple of joystick ports. And that's the heart of the machine from a logic point of view. What can I do with it? I had a look around on the internet and I found a very vibrant homebrew community. Lots of people writing their own games and programs, making new add-ons to it, 3D images, flashcards, all sorts of stuff. The thing that really turned me on about it is that it's got a very simple memory map and the cartridge port exposes all of the data buses. So you can do a lot with it without even taking the box apart. And I thought, I can put Camelforth on this. Sounded like a good idea to me. But in 2016, there were some challenges there. The first was that the Vectrex has no serial port. I knew nothing about 6809 assembler or any assembler, to be perfectly honest. When I did fourth program in the 90s, I was an applications guy. I didn't really get involved with the low-level stuff. I didn't know anything about the Vectrex BIOS, which is in there, and I didn't know anything about low-level forth. So quite a few challenges. So I decided to define myself some goals. The first was to get Forth running on the Vectrex with an interactive terminal, something I'd never done before, never brought something up from cold. No hardware modifications to the Vectrex because your average user of a Vectrex is not going to open the box, full stop. my fourth must provide an API to the BIOS, because it's the BIOS that's got the machine code routines for writing to the screen, reading the joystick, making sounds. It had to be comparatively fast with assembler and C, not something that's a toy. I didn't want it to be like BASIC, where someone will have a play with it, realize they can't actually do anything with it because it's not fast enough, and then forget about it. That wasn't really that's not my aim. And the fifth one there, to be accessible to new potential developers. There's no point doing this on my own. It's great to have a community, and that's the whole point of doing it, to have fun with other people as well. So step one, configure the CamelForth for the Vectrex and cross-compile. So this was messing around with the memory map settings in CamelForth and give it a compile. Sounds fairly straightforward if you've done it before. If you've never done it before, that's a daunting task. First thing I found was that CamelForth was written using F83 and needed DOSBox. I thought, no one's ever going to use DOSBox, a new developer, not going to happen. Need to change this to use a Windows or Linux program. Luckily, somebody had already converted it to run under GForth. So that was a win. Second thing, no block files. No new developer coming to Forth is going to use block files. I don't think that's ever going to happen. So I thought I need to change this so it can use plain text files. So I thought about that a bit and managed to make it work. A few other changes I made to CamelForth was make it case insensitive. It was driving me nuts having uppercase all the time. My keyboard, when I type on it normally, is lowercase. It's as simple as that. So I was no way I was having uppercase. Number-based recognizers, they saved a bit of time as well. They were very handy. Next part, you can see here the memory map for CamelForth on the left-hand side here. The memory map for the Vectrex is on the right. So you can see at the bottom, there's 32K of ROM space. There is, down the bottom here, you can see, I don't know if you can see because I've got no laser pointer on. I've got a laser pointer on. If I can. So you can see over here, is there a laser there? Can't see a laser.
Not seeing.
Yeah, there we go. So
oh, yeah.
You can see the ROM, which is another name for the BIOS, is right at the top of memory. And then what that then does is it does some reset on the vector monitor, recalibrates the joystick, that sort of thing, and then jumps to near zero to run the game ROM or whatever it is that's plugged in. If there isn't one there, it runs a game called Mindstorm, which is built in at E000 hex. There is a 1K RAM on this thing, and a chunk of it's used by the BIOS. So you've got 896 bytes to use. All of this Forth dictionary, parameter stack, and everything else managed to fit in there and gives me a huge 256 bytes of dictionary space to use, which is actually enough for doing what I want to do with it, because CamelForth comes with a cross compiler. So the amount of RAM you need is not actually that much if you're just using it for testing, which is what I do. Okay, so what else have we got? Yeah, I just wanted to introduce the Vectrex IDE. So this is a program that's written in Java by an enthusiast in Germany. It's a fantastic program. It's got an emulator. It's got an assembler and also a C compiler built in. It's got a full debugger on it, which is really useful. And additionally, it's got this thing over here called Jakacki, which is really useful. It allows you to put in 2 addresses and it will tell you how many cycles have passed from when it gets from one address to the next address. Now that becomes really important, which I'll talk about that a little bit later on. So what that allowed me to do was to, given my Vectrex had no serial port at this point, I was compiling code to the Vectrex in Forth, and I had a Forth program. How do I know what it's doing? So I managed to make it call a BIOS routine, and I managed to single step it using the debugger. This is a really early picture of it, but you can see you've got key query, and emit down the bottom here. You've got next in here, which is jump y++ in brackets. So I could see the code, and this was all new to me. I'd never done this before. And I managed to step the thing through, and I hacked cold such that it didn't run an interpreter. It just ran a BIOS function with a string hello world, and then it ran it in a loop that went up and down. And it worked, which was quite cool. So the next step was putting a serial port on this thing. Now there's a cartridge on the market. Well, it's not really on the market. You've got to know the guy, actually. It's very difficult to get hold of one, called a VecFever, which is an STM32 ARM processor, which emulates an EEPROM and does a whole bunch of other stuff as well. It can actually take over the whole of the Vectrex and basically just use the UART to control the monitor and joystick and keyboard. It's a very, very powerful computer. You can do some amazing things with it. It's also got a soft UART in it. So I rewrote my emit key and key query for the soft UART and unhacked cold, and magically Forth works. So you can see here with, I've got Teraterm running, we've got Vectrex Forth. This is from about a year ago when I got this. Well, I got it going before that, but this picture is from a year ago. And what this is showing here is that I've got Camel Forth down here at the bottom. At this point, well, I'll come on to this in a minute. You can see that it's saying here, I've got a BIOS API here. So I can now, I've got a written BIOS here and some test words. I'll come on to them in a minute. So the project goals at this point: get Forth running on Vectrex with interactive terminal, done. No Vectrex hardware modification allowed, done, because it all goes via a ROM chip or an emulator that plugs into the cartridge port with a serial port added in. Next step, Vectrex Forth to BIOS API. Done that as well. So you can see the code that I've written here has got things, for example, cold start, warm start, vector monitor calibration, direct page manipulation on the 6809, special feature it's got, joystick, sound and music. This is about a quarter of the BIOS functions. There's a whole lot more than this. There's no factoring in any of this, or there's no macros in the Camel Forth assembler. Therefore, it's all a lot of cut and paste in here, but it does work. And at the moment, I've got enough space. It doesn't really matter. So Vectrex Forth to BIOS API test. So to check all this lot works, you obviously have to test it. I've got some pictures of here of some tests. Now, with a bit of luck, I can show you some of this. So I've got my code over here. I've got a terminal up here. And I have got a, now what I'm going to do, actually that's not going to work. I'm going to cut my camera off so I can show you my camera. Actually, the camera was already working, wasn't it? Let me just show you another one.
Okay.
There. Okay, so you can hopefully see some code. You can see what's going on here. You've got the Chromium Cross compiler, which is running under GForth. Then you've got the Camel Forth memory map and some synonyms. All of the Vectrex code, which is the music data, some header code that if it's not there, the BIOS won't work. A bunch of vector lists, which are the addresses of the shapes that you draw on the screen. Some serial I/O code, Camel Forth itself, and then a lot of BIOS related stuff. So that's really what's being compiled here. So I mean, I've got it running already, but I'll show you how it works. Basically, you can compile the code, and it's done. You can move into a mode where the VecFever cartridge, it's in the Vectrex, is waiting for a file to be downloaded to it. I download it pushing this button up here, which says VF. That's copied it over. It basically comes up like a thumb drive, USB thumb drive. So I've copied the code on, and then if I eject that thumb drive, it starts running, and you'll see I've got a Forth prompt here. So to show you a few of my test words, I've got, for example, let me try this one. This is a sound one. You won't actually see anything, but you might hear it. Can you hear that? So that is the Commando high score theme tune stolen from an Amstrad CPC, I believe. What else have I got? We can do, so there's various different music player bits of code we've got here. Actually, I suppose I could show you, couldn't I? BIOS tests. So that's a little music player I've written here. It's not very long. Is that the one? Yeah, that's it. That just did that tune. What it basically does is it takes a bunch of data that's commed into memory and then runs it on a loop through the sound chip. Fairly straightforward. What else have I got here? Here's another test. You'll actually see something here. So this is an intensity test. It does some concentric rectangles to the center of the screen, and then hello world in various different intensities to show that works. Let's see if I can show you that here. There we go. That's the code for that. So yeah, I mean, I won't go through all of this specifically, but you can see what it's doing. It's got a begin until loop where it just prints some stuff on the screen and a string. Fairly straightforward. What else have we got? Vectrex is a vector system, but it also has raster graphics. So it does raster versions of code. These are BIOS calls, by the way. So I'm giving the BIOS a string in memory, and it's rasterizing it onto the screen. Let me see if I can find those. That's, try again. that's the code for that. Fairly straightforward. Does a recalibration on the screen, sets the intensity, and then just prints some simple BIOS calls with some simple memory locations for the text. And that's all the text up here. One or two more to show you. There are some built-in, because it's a vector system, you don't have squares so much. You can do circular stuff. So, for example, there are sine wave tables built, or sine tables built in. I can very quickly show you one of those. There's a sine wave on screen where it just uses that data. Additionally, I can do a rotation of a vector list using RVL. And you can see some. It's nice and smooth on my screen. It probably isn't on yours, but there's some turtles going around together in synchronization. That's the code to do that. There's a begin until loop again, and it just prints one out and then prints another out using a slightly different printing method. So it's testing a bunch of different things here, ways of drawing to the screen with different BIOS calls, different intensities, that sort of thing. What else have I got? One or two more. There's some score functions that use binary coded decimal. So it stores the score in a string, maybe 5 or 6 characters. You can do comparisons of 2 strings from a score point of view. You can do updates, that sort of thing. This is it showing you there's just some simple tests. And last one I've got here, hang on, a couple more. Draw shows scaling of vectors. So you can draw things big or small, fast or slow. And there's lots of different methods you can use to draw the same thing, depending on the vector list you've got and where your current beam position is, and what registers you're using. So yeah, that's those. One more I think is the object hit. So if you've got some objects on the screen, this is showing. Just look for those. So this is a number of different tests here where you're giving it vector. Basically, you give it a box where you expect the thing to be, like a bullet, and another box, your ship. And you give it 2 boxes, and then the hit functions will work out whether or not they overlap, and therefore whether or not there's been a hit or not. So they're quite useful. They're the sorts of BIOS functions that are in there. There's a bunch of other stuff as well, which is not so interesting to look at. So yeah, that's all the testing that I'm pointing out on here. So project goal number 5, is this accessible to potential new developers? Yes, it is. It's on GitHub. Last bit then. So what happened to project goal 4? Must be comparatively fast compared with assembler C, not a toy. So the Vectrex has a 1.5 meg 6809. The monitor needs a 50 hertz refresh, and there's no screen buffer. The CPU has to do all of it. So if you've got 1.5 megahertz and a 50 hertz screen update, if you go lower than that, it flickers like crazy and looks horrible. If you go over that, everything wobbles for some reason. It just does. It has to be 50 hertz. That means you've got 30,000 CPU cycles to get everything done. You have to update the screen, read the joystick, do all your game logic, do the sound. There's quite a lot going on there. Drawing vectors is quite time consuming. It's quite a primitive way of doing it on here with the way the DAC works. DTC camel forth is not optimized. That's also got lots of cycles. So if you want to do lots of things on the screen and lots of other graphics and sound events, you have to think outside the box a bit and do some smart things. That's all possible, and I've done quite a bit of it, but I don't have time to talk about it today, so maybe you'll hear about that next time.
Fantastic.
That's
really great, Philip. Thanks for that. I love those vector graphics displays. I remember as a kid playing video games, and we always gravitated towards the vector machines, because they just look so great and they're so smooth and all that sort of stuff.
They're a bit special. That's true. Absolutely.
Yeah, they are. Absolutely great.
Good stuff. Hope you enjoyed it. Thank you.
Thank you, Philip. Fantastic.
Okay. I wonder whether Peter is going all right.
I've got some faulty hardware here somewhere. Just something funny's going on, and trying to sort that out. I'm just thinking plan B at the moment if I need to, but if I can just get this up and going, that'll be really great. Because I've got everything set up for it, you know.
Okay.
So that's what I really want to do. Okay, so if anyone else, can anyone else go now?
I think we have Demitri. Demitri has a presentation of FPGA CPU, which is a fantastic port of DON CPU for the VHDL, I think.
Yeah, that's right. I can share that. See if I can figure out how to do that.
I see we have Ilya also in the meeting, so later we can follow with Ilya if you are ready after Demitri.
I'm almost there. I'm just trying to figure out how to go full screen and also share it. Okay. Great. Can you now see my presentation?
Yes.
Good. All right. So I've been working on a fourth CPU, which we tend to put on an FPGA. Originally, it was Don's work. It was written in VHDL, and I took it and I started translating it into System Verilog and doing things a bit differently. And we came up with a few ideas. So I'll be presenting the ideas in this presentation. Good. So why do this? Why do a fourth CPU on an FPGA? Well, there's two parts to this question. One is the FPGA part and one is fourth. So one of the good things about FPGAs is that they are flexible. You can prototype a number of different designs before you settle with what you would like, rather than having to play around with chips that you put together, or with an ASIC with a proper silicon chip that you manufacture. You have a lot of things you need to get right, and then you manufacture a large number, and if you made a mistake, it's very expensive. So this is why we've gone for the FPGA. And another thing it allows you to do is you can add extensions to the design. So a person might receive the processor as a HDL file, and they might decide to add things and put those things on their own FPGA. So it gives a lot of flexibility to the user. The second point is that fourth can now be executed in hardware rather than software, because the FPGA is simply acting as hardware. And this gives you speed and simplicity. The reasons why are because instead of fourth words being executed as assembly instructions for some other processor, each instruction can be equivalent essentially to 1/4 word. So you're pretty much executing fourth directly on this processor rather than trying to write a sort of interpreter for fourth. And it's simpler also for that reason, because you don't have to make a switch from fourth to some other architecture. It's still fourth at the hardware level, so it keeps it all quite clean and simple. In Ilya's presentations, he has given some really great reasons about why fourth CPUs are so powerful. So check those out if you would like, but I'm just touching on the surface here. The final point, which is quite different, is I want to show that fourth is complete. I want to show the power of fourth, because we see a lot of fourth implementations implemented in C or C-like languages, and also fourth implemented on C-like machines. So you don't have to do this. You can have fourth going all the way down. You have a fourth language which runs on a fourth CPU. You don't have to make that switch, and I want to show that in this project. I'm not the first to show it, of course, but it's one of the things I want to illustrate in this group. And about the hardware, C machines, well, what is quite interesting is when I found out about RISC and RISC-V. I currently work in the area of RISC-V, and oddly enough, when you read the specifications, when you look at how they've designed the architecture, it suits itself to C. These processors are more designed and optimized for executing the C programming language. And one of the benchmarks really is to get Linux running on it. So a lot of the hardware we have is geared that way. But I want to show that Forth can actually run on a Forth machine, and this Forth machine works. It's also very compact as well compared to some of these C machines. Even the RISC-V processors, you'd be surprised how much area is taken up even by the simplest ones, because they have to decode all the instructions, they have to manage the pipelines. There's a lot of extra things that start to build up. Okay. So how is this going to be different from the other Forth CPUs? This is of course not the first Forth CPU, no way, and it's not the first on FPGA either. There have been a number of other attempts and working products that are used. The main difference here is we are looking to write this at the behavioral, in the behavioral style of code rather than RTL. So what does that actually mean? And I'll try to give my best to give a description now, but I'll show you some code later that will illustrate it better. But most Forth CPUs are written at either logical level or the component level. So you either have a description of all the logic gates and how the logic gates connect up, which is fine, or you have some components and the components get instantiated and you connect up all the components. But these are very low level ways of thinking, and a lot of the time it's hard for somebody else to understand what the hardware is doing. The advantages, of course, is area, control over area and performance. But we wanted to experiment with writing this CPU in the behavioral style, which almost looks like a language like C, because you are now bringing it to a very high level where you don't describe what the hardware is, but what it does. And you allow the tools to then go and figure out how to implement that in logic gates, how to implement that in the hardware. This is a real technique. It is used in the industry. I've seen a lot of code written this way, and it does synthesize and produce products that sell. This kind of feeds into the next part about easy to add extensions to, because it will be easier to understand, easier to read. We're hoping that this will also make it easy for others to add extensions themselves, or at least be able to suggest them by reading the code if they're not confident to make these changes. And we plan to keep that in mind as we build it. Other things is that we might deviate from standard Forth a little bit, because our goals now is really bringing Forth to a higher level and also using it for robotics and artificial intelligence. So there might be certain things added that are not normally there by default in Forth, such as lists. We might implement some list primitives in Forth, symbols, dynamic type checking, because you can use some bits. You can use some bits of the words to indicate the type of the data, and then you can do dynamic type checks. So that would solve the problem we're talking about in one of the meetings about floating point versus integer, because you could do a kind of dynamic comparison and conversion and so on. These are just some ideas. We're not necessarily planning all of these at the moment, but it's just to give thoughts and directions we might like to go in. So how do we plan to verify that the CPU works correctly? Because this is something you do have to give Forth to. I am a verification engineer. And probably the most likely method for a project of this scale, which takes advantage of Forth, is to develop the CPU quickly to the point where you can communicate it over serial, and then you can do interactive testing, because each time you execute a fourth word, you're exercising part of the hardware. You can verify that it works very quickly, and possibly, although you have to go through the synthesis and loading process, if you make a hardware change, if you have a ROM or boot ROM, which perhaps has some fourth words or microcode, you can actually update that once you have the design on it as you are testing. So that could provide a quick way to make some fixes and bring up the design. So this takes advantage of Forth, because Forth can be bootstrapped very easily and it's interactive. The more traditional way might have been to use system Verilog test benches, and you could have some directed tests which do some very predictable behavior, put some things on the stack and add them or subtract them with a result. And a more advanced version of that would be to test with a high-level reference model. So you could have an kind of abstract version of the CPU, and you run Forth code on both of them, and you check that they behave the same way, that you get the same results from them. The very last one, and this is not likely to go ahead, it was one of the early ideas I had, which was I was actually thinking of writing a CPU reference model in Forth. And the advantage of that is that it would be interactive, so you can test parts of it interactively, all in Forth. And then the idea, which sounds crazy, but I think is more plausible than it sounds, is to compile that Forth into system Verilog. It might not be able to compile into all of it, but maybe pieces of it could be translated, because if you limit those constructs of Forth, all you pretty much need to do is convert things from a postfix notation to infix notation. However, I think this method would probably require a lot of work. You're gonna have to work out how to do all that translation. The first point is the most likely method in terms of how we bring things up right now. Oh, great, okay. So I will show some things now. I'm going to compile the processor in Quartus, just to show you that, well, I'll give you a little look at the code and also show that it does compile at the moment. Yeah, it is incomplete, I have to say. We are still working on this project, but it will give you a taste for it. So I'm going to stop sharing and open that up. Where's the share button? Okay, what I might do is, okay. So here is Quartus, because I am using Altera tools. I don't know if, can you see my camera at the moment, or is my camera hidden because I'm screen sharing? Someone let me know.
We can see you.
We see both. You're at the top and we see your code.
Okay, great. So you can see both, right? So yeah, I'm using a Altera FPGA for this project here. Okay, there we go. Here is my board. It was very cheap. It's probably around $20 right now. So it doesn't have to be expensive. It definitely holds a Forth processor, because I've loaded the EP16 on it, and you can actually instantiate multiple of these processors, and you still got space left. So we have the possibility of doing design with multi-processors, but yeah, we're also keeping an eye on costs so that it's not too expensive for others to get into. I don't know how readable the text is if it's too small. It's good. Okay, that's good. So yeah, I'll go through it here. Otherwise, I would have brought it up somewhere else. But let me click the compile button, and we'll see if that works. So what we have here are parameters, so you can change the address size, data size, and so on. And we have some codes. Now, there is a way to represent these codes at an even higher level, which I will show you after this, but this is good because you're giving names at least to these numbers. We don't want too many numbers in, oh wow, that was very quick. It's compiled already and passed that check. So syntactically, this is correct. But yeah, we want to almost eliminate numbers, or at least reduce them as much as possible. So we give them names instead, and these are the names of the instructions. And then you get down to the implementation of code itself. In System Verilog, you can use logic. You don't always have to use wire or reg, so that makes things a bit well, it's easier for me personally. And what we actually have here are tasks. So these are almost like procedures. Same way you have like a function in C, or you can liken it to a fourth word. And if you notice, they each do things like push data on the stack or pop data from the stack. This is the level at which we're writing things. And believe it or not, although these are to our eyes functions that would normally be called in software, the synthesis tool can translate this into logic blocks. It can translate it. It is quite surprising if you've not seen it before. This here is our boot ROM, which we are still deciding exactly what we'll do with it. But some of the thoughts have been that we can have perhaps the inner interpreter here, or code for controlling the serials for your communications. It's basically anything that you want to run when you start up the CPU. But we also might think of having some words defined here. And this could be the place where we define things such as the list primitives. You might have your cons equivalent of const-car CUDA, if you know Lisp, defined in this boot ROM here. And this bit you can change without modifying the rest of the hardware. It's a little bit like microcode, but not exactly. There's some differences. Otherwise, you can implement the words in hardware itself, but it may be too difficult at times. So that's why we also have that level. So let's go down and have a look at the instructions here. So this execute task is what does each of these instructions. You notice that the lines are very short, they're very high level. There's no feed this into this logic gate, or bit slice this or that. These are pretty much how you'd write it if you were modeling this in C. So hopefully that is a lot easier to understand than some other implementations, although it may have costs in performance, which we're willing to take for this. So that's what we've implemented so far. And then you get down to this part here, which is main loop. And when you restart, the opcode is run boot, so it puts it into boot mode, which means it executes instructions from the internal ROM. And then when it reaches an instruction called end boot, it will switch over to any other memory to execute code from there instead. So this was one of Don's ideas. Okay, so now that I've shown that, I'm going to show something else, which is just illustrating some of the changes you can make to designs to make them more readable. I'm going to show the J1. The J1, it was one of my, I really like the J1. I've not actually used it on an FPGA. I've used the EP16, but I like how concise it is. It is very, very concise. So let me show that, and I'll show you what I did with the J1, rewriting it in System Verilog. So, oops. Let's share screen. And can you see Notepad++? You can, okay. And I might make the text just a little, no, I'll keep it here. That's probably fine. So I believe this is the original J1. I don't think this is one I've modified in any way. This is how it looks in Verilog. So I'm just going to kind of scroll through here. you know, so in Verilog, you've only got wire and reg. You have to keep track of which one is which. But in system Verilog, not always, but you can usually use logic instead, and the tool works out whether it's a register or whether it's a wire. But notice there's some magic numbers. What on earth are these magic numbers? What do they mean? You do have comments, but you quickly see that there's bit slicing, there's undocumented numbers here. You know, how would you know what this case statement does necessarily? It's hard to tell, although it's very precise what is happening, but it's hard to tell. You wouldn't necessarily know just looking at it how you would add some new functionality, right? Now let me show you what I did when I translated this to System Verilog. In System Verilog, you have things such as types, so you can have create enum types, which allows you to give names to numbers automatically. And if the numbers matter, you can assign them. You can say like jump equals 1. But here I've just let the tool pick because we don't really care. We don't actually care which value represents jump, which value represents branch, call, or ALU. It's not interest. That is below the level we're thinking at. And these are the basic instructions, the format of the instructions and ALU operations. So let's have a look. You notice here, I'm using just logic all the way down. And so here, remember I showed you this before. You just had some, let me go back to it actually, so you can see it side by side. So here you just had some numbers. Yes, you had some comments at the end, but how about this? You know, you name each part of the case statement and you say, okay, well, this is a jump, this is a call, and this is a branch. This is an ALU operation. It's immediately clear what is happening when you look at each part. And here, if you remember this case statement, you now have names for each of these operations. You know what it's actually doing. In Forth, you recognize things like dupe, over, add, and, or XOR. So these are some of the, even down here, let me go down to that part because I was not thinking of that. Again, looking at this, you may not immediately be able to tell what it does, but in here, look, you say instruction equals branch, instruction equals call, and it continues like that. So the J1 has been designed at a low level to begin with, and I'm trying to bring it to a higher level, which this is subjective, but many of you might agree it's made things a little bit more readable. You can go so far with that. What we're planning to do is start from the high level and go down. If we find that timing doesn't work or logic paths are too long, then we work and cut those down, but we start at the highest level rather than coming from the low level up. So that is that. Let me check if there's anything else I wanted to demonstrate in this part, or else I will finish. The only other thing I'd mention is that the processor I was working on here is a bit of a hybrid at the moment. This is our processor, because I was translating it from VHDL and things haven't fully been moved over yet. I think I might like to use the enum idea for this, and you just create an enumerated type instead, because the codes for these instructions are not that important. It doesn't really matter as long as they're unique, they're symbols. So that's one of the changes, and I'll go back to my slides where I explain what I want to do next. Okay, so we should be back to my presentation if that worked correctly. Good. Please advance. So Yeah, well, so one of the things we'd like to do is replace numbers with enumerated types or perhaps parameters. Parameters are another simple way you can give names to numbers. We want to add the remaining fourth word set because we've only implemented some of the words at the moment. And we need to add modules for serial communication. At the moment, the processor has no way to communicate with the outside world. So we want to get that in as soon as possible so we can begin interacting with it and testing. This will require the bootstrap code and the inner interpreter to be written. And I'll just take this moment to mention that Ulrich Hoffmann has a great tutorial on writing an inner interpreter. He actually shows how to do it in Forth. And since we are now thinking in Forth, we can all understand this inner interpreter. So I'm looking forward to doing that part. And I believe that is it, actually. Yes, that is the end. So do we have any questions? Oops, I think I've...
So can you add AI extensions? I think you mentioned that with Lisp, but we could add Prolog and things like that, maybe?
Absolutely. So either in the boot ROM or in the hardware as hardware instructions, you could implement probably not the whole of, you wouldn't want to implement the whole of Lisp or the whole of Prolog, but there might be certain primitives in those languages that you want to add so that you can basically write those languages in Forth. So you have the same capabilities that they have, but it'll be in Forth instead of exact copies of Lisp. Although if you wanted to, you probably could just implement those languages, but we're trying to keep things in Forth.
Just one question that might be silly or not, I don't know.
Questions welcome.
When you're adding lists, would you need to add another stack for those lists?
What we'd probably need, that's a good question. So would we need another stack for that or not? I would say that is an implementation decision you'd have to make at the time, but I think what we would want is to have support for garbage collection so that you can create lists and you can dispose of lists as you want to, and you still have memory left. So the advantage is that the garbage collection could run in parallel because we're working in hardware. And so that is one thing I did mention, being able to use the power of parallelism. And in the probably distant future, you might even consider having multi-cores. Each core is doing its own individual thing. These cores may be of same instance of this processor, or we might use a few J1s because they're so tiny, or EP16s or 32s. It depends. There's lots of possibilities.
So like a heap more than a stack then?
Yeah, you could definitely implement the heap storage. I'd say it'd be an implementation. Something that you'd probably want to model first, do some experiments with, and then you can decide. But the good thing is if you take one approach and it doesn't work on FPGA, that's fine. You can undo it. You can try again and reload the design and try a different approach.
It's way cool anyway.
Thank you.
Fantastic, Demitri.
Yeah, I just want to say you got the idea. You are aware on this way.
Oh, yeah.
It was great.
One question. I've never worked with an FPGA before. When you load your software, is that as quickly as loading microcode on like an ESP chip or something? Or you just copy a file to or hit the upload button in the IDE and it uploads it to the FPGA?
Good question. I would say that, yeah, from my experience, they're about the same speed. It takes about the same amount of time, It does depend on the complexity of your design, of course, and
right.
The same way it would depend on the complexity of your software if you were working with the ESP32. But yeah, it can be done in similar time frames. So realistically, you can upload it, play around with it, make a change, and in probably for something of this scale, in maybe 5 to 10 minutes, have another one on there.
Excellent. Thank you very much.
Well,
No problem.
okay, guys, we follow with the next participant is Klaus Kohl Schöpe from Germany. And this is the first presentation of Klaus. And I welcome him very much in this Zoom meeting.
Thank you. I think you see my presentation and also me. And you see also in the background a lot of documentation. Because I'm working since more than 23 years as a microcontroller specialist here in Germany next to Augsburg, and supporting all kind of technical question around microcontroller. And because Arrow Electronics is the biggest distributor, I have nearly all kits here. So I think altogether there are some thousand eval kits which are available for me, and partly I give it also to some other people. My history for microcontroller is very long, because 1978 I start with the first programmable PC, and even during my first work I have the first contact with FORTH, and so I work now nearly 35 years with FORTH, but I think I have a little more history here in the presentation. Private, I'm married and have one son, all in the house, so we live all together. Here is my history for the work. I begin with a ground school in Germany, and then beginning training for the laboratory assistant for chemistry next to here. And then later I decide not to work as a laborant. I work more as a student and developer. And that's the reason why I go to the technical school. During this time, it was necessary to go to military. So I spent also 2 years at military before I begin my study for technical physics. And during this time with physics, I had the first contact with my later company, BNC Dr. Schetter. And it was also my first contact with FORTH, but later more about this. And with this company, I worked from 1984, I think, up to 1998. And then I moved to the distribution for microcontroller and so on. And normally I focused on microcontroller, but next to it, I also cover some of the peripheral like memory, sensors, and physical interfaces, and also software stuff. And because of this, I have a lot of kits which I also give to interest people and people who want to implement FORTH on it. And during the last time, I also have a little more activities with FPGA to realize something. So in the FORTH history, I had the first contact at BMC with a small calculator called Sharp PC 5000. It's a Sharp processor, which has normally BASIC on it. But there are a small company next to Munich who offers also FORTH for it. And because I had the problem with the speed of BASIC in a customer application, I moved to FORTH. And this was my first contact with FORTH. And also my interests are rising more and more. And it was also the time with first contact with Forstgesellschaft in Hamburg and also in Munich. And I was more and more involved in activities around the Forstgesellschaft, as some people know. And I cover distribution for any force documentation and force version, for example, the Volksforce. And in the beginning, it was also a move from the management of the Forstgesellschaft from Hamburg, from Klaus Schleisig and other people, to Munich, because in Munich there are some people who are also very interested in force and working with his own company. So he has a big experience how to handle a company. And that's the reason why we moved the management during this time to Munich. And especially Heinz Schnitter, who are managed company, has in accelerator laboratory in Garching, many boards used with Zilog Z80 on it. And that's the reason why we had a lot of contact with Zilog, with Harris. And so we developed some boards for it. Later, I developed my own force version, KK Force, which is based on the standard 83 force. And I realized it on Z80 on PC and also on some other boards like RTX 2000, because I use it during my work for measurement system. And also for the Forstgesellschaft, we realized some boards with RTX 2000 on it, but later more of it. And also during this time, Zilog asked us to realize a ROM force for the Super 8. It's a modification of the Z80 processor, Z8 processor, which has nested code optimization. And then it was very quiet because I had a lot of work and a lot of activity, which is more in the range of C compiler or a lot of assembler. But later I start again with a new first version, which is easier portable for flash version. And during the last 3 years, I'm working a little more on FPGA because we had some very low cost FPGA board here, for example, for the Max 10 Intel. And so I also do a modification for the J1 processor because I don't like a processor which has 16 bit per address. And so I moved to 8-bit address and some improvements for the force itself. And this is done for the Max 1000 board and also for the Cyclone board. As I mentioned before, I had very early contact with the Forstgesellschaft. Even in 1985, I was on the first Euroforce meetings in a castle next to Stuttgart and also in England. And later, I still do the support for force development with some kits. For example, I send a lot of kits to implement different McRISC versions. And now I'm working with Feuerstein group using the first RISC-V boards. Back to the history, my first contact was really on Sharp PC5000 with BASIC and Force, because we realized a measurement system which was used in many customer-specific applications. And one of the applications was German Telecom, who want to know which errors are arising during this transfer of data. And so we realized this MC12A board, which are really use only this processor. So I get sometimes question how many power he need for one multiplication, because during this time it was very difficult to export such boards to Eastern Europe. And so we was limited to 8 kilobyte of ROM and 8 kilobyte of RAM. So it was very limited system. Later, we moved to a Z80 system, which was my first own force, with a small display, with a separate keyboard, with a printer in it, and a disk drive. So you can really measure systems with up to 8 channels and do calculation during the measurement and doing control. So it was also used in a lot of application. And in parallel, I implement my force on different architectures. And for example, Electronic Lab in Germany sells this force together with some of this board. Not many, but it was interest for me to realize it. And this was also the first contact with force processor from Charles Moore, because before I realized the sequencer with microchip PIC 16, which is very difficult and very slow. But with NC 4000, it was much faster. And it was also my first contact with Charles Moore force. And I thank Ting about his book, because it was a big source for my force and my application to understand force a little better next to the books I have. Later, we moved from NC 4000 to the RTX 2000. So I really have those boards here. So I can, even now, I work with these boards. But this board was with a ROM version and with a OTP. And that's the reason why I only use the ROM to start up, copy it in the RAM. And then if you save the system, I program it back to the ROM. And so this board was done by Dirk Brühl. I still have contact with him. And so we have a very long history. But then after this Zilog activity, it was a long time, which I do nearly know activities with force. But you see, I'm still a collector of hardware and software and documentation. And that's the reason why I also have this Delta T FIP 6000 processor, which is a processor from Klaus Schleisig, and some other boards. And for example, this is a Z80 or 84C015 Z80 board, then a special processor with force and ROM. And now I'm working more with FPGA to realize my own IP and maybe 6502 on this board. But as Max 10 on this board are very limited, so I have to realize all my application in 32 kilobyte RAM. But I'm still a collector, so even I have 2 chips of green array, but I have no time to bring it to a board, and 1.8 volt technology is not so easy. So, as I mentioned before, I do some own force version. KK Force was based on the Force 83, and now my newer force are improvement for the Force 83, more direction ANS force. And to realize it, I decided to implement a virtual processor for the PC and transfer this technology to a standard processor like Cortex M0. And what I do is really to implement a processor which has one memory, which is divided in flash and RAM, maybe together, maybe separate. So even 8051 are possible with this force version. And I have the normal registers like PC, stack pointer, return stack pointer. And normally it's easier to handle the top of stack and top of return stack internal to be a little faster. But I also think about the nested processor, and that's the reason why I have also the IP register, which are pointing to the actual force program and the working register. So it's a really simple model of a force system. And it's also a simple count of commands. So you see, there are only 64 commands which are used in this processor architecture. Some of them need additional relative address or values. So it's depending on the implementation, like 32, to add next to the 8-bit code an offset or an address. And then stack operation, return stack operation, logic operation, memory access, program memory access, IO access are separated, and extended address using a double address to reach external memory. Then the indirect threaded code needs 5 opcodes, and then moving directly to the assembler code of this processor, calling the system for maybe disk access and so on, and NOP. So with 64 opcodes, I cover the whole force system for nearly all devices. So I have only to implement this to have a complete system. And in many cases, I use also some history things from Charles Moore, like the next architecture, but I modify in my version that it will only start with 1, and if it reaches 0, then it finishes. So it's only a short overview about the system and a little about my collection. You see on the website of Force-Gesellschaft, this is my bookstore for force literature. So it's a lot of books. I have also a website for my MC Force for the PC and for the XMC 1000 family. Also my modification for the J1 for the FPGA is here in source code with compiler, simulator, and all kind of things. And during the last time, with the support of Peter Force, I start to update my list of force system, which is also available on this website. And you see, I have nearly, I think, 150 different force versions here on my PC. So there's a lot of Volksforce, McCrisp version, and then FigForce, and of course eForce is in my collection. So if you're interested to, if you look for any software, please let me know. Normally I collected during the last 35 years. So I think that's all what I want to mention about my life with Force and my life with microcontroller.
This is amazing, Klaus. Fantastic. I bought from you in the 90s, I think.
Yeah.
The Super C8, some samples.
Yes.
I received from Zilog directly from Taiwan, the first ones, and then later I bought in Germany from you. And we use these processors for CNC machines. It was very fast, very fast processor for its time.
Yes, it was good. But later with a standard processor, which supporting is also and are much faster, like the 86,000, the people are moving more to the high-end version and to the PC and Linux and Windows area, but I'm still a microcontroller fan, and so I try to support all kind of activities in this area.
Fantastic. Please, Klaus, if you unshare your screen, so we move on to the next participant, and you are invited anytime for another speech. So just tell me, Peter, I will present. I have an idea. I want to present. I want to extend some information. You are always welcome.
Oh, I cannot open the windows.
So I'm getting there with my stuff too, by the way, Peter. So yep. So
Yeah.
just letting you know.
Okay.
Are you ready, Peter, now? Because I was expecting Ilya, but I don't know if Ilya wants to speak later.
I'm ready.
But who of you, either you or Peter?
No, that's good, because I'm fixed up a couple of things here, so I've got one other fault I have to fix up. So please go, Ilya.
Okay,
Thank
okay,
you.
Okay.
we go.
Okay, so I will start.
From let me introduce you. We go on from Germany to Australia and then to Moscow. Ilya Tarasov with Write Your Own Force Compiler.
Okay. Can you see my screen?
Yeah.
Yes.
Okay. So this is part 4 of my combined lectures. Okay, wait. Okay, where we are. Why? Because previously we successfully launched a simple fork machine, and now we need. Okay, just let it be so. And now we need to connect it to some kind of software application and see what happens. What I plan to explain now, how to write a simple PC application with a Ford virtual machine inside. And this will be just the first step. It will be obvious later why it's just a first step, because results will be not so good. And also, we have a C code. And I was slightly surprised, but only slightly. I'm expected some fixes for Arduino platform. But our 700 lines of code successfully compiled in Arduino with no changes. So we can add this fork machine to an Arduino platform. And finally, how to convert our fork machine into a large and serious software project. Okay, PC application. PC application. It's very easy. We just need to connect our Ford header, so include Ford header to our simply console application, and I can run it. Where is it? Where is it? Okay, it's executable file. Oh, okay. 2 and 2 plus 4. It's very simple and very obvious, and looks slightly boring. We have only console. We have very limited access to our PC hardware and libraries, and something is wrong. Let's try to connect to an Arduino. And can you see my camera as well?
Yes, Ilya. Yes.
Okay. Okay.
Yes.
Very simple. Arduino, it's Bluetooth enabled. Arduino Nano. I can connect it. And this is my code. FORTH virtual machine is included. And very, very simple application is done for an Arduino board. Okay. We can download it. I especially want to show how it working, because we need time to compile and we need time to download it to our board. Okay. Okay. Now I can 2 and 2. Oh, it seems, yes, I have implemented addition. And what we need here, we adding our FORTH machine to our software project. We initiated vocabulary to create linked list with pointers to our functions. We can add specific words from Arduino platform. For example, we have a digital write. Okay, this is our FORTH digital write. The only difference, parameters are reading from the data stack. Okay, it's not a problem. I know it will be 1. I know port number 13 is an LED port, and okay, we can see an programmable LED is switched on. Okay, let's switch it off. Now we can rule our Arduino board. This is the same virtual machine we wrote for C++. So it just ran it under Eclipse IDE. It's running under Arduino. And now we can rule the entire Arduino libraries just by connecting. I see. I can show init vocabulary. It's creating a base FORTH vocabulary. And we can adding words with a name and a pointer to our Arduino function. The only limitation, function must be void type and accepting no parameters. All parameters must be reading from the data stack of our connected FORTH machine. That's easy. And I spent about 20 minutes to run it. More interesting, this is ARM Cortex-based board. And this requires about 180 kilobytes of memory, because all FORTH is not in the flash memory, it's in the data memory. So linked list and FORTH data array, both are in the RAM of our platform. I have no goal to compile it for a flash memory of Arduino. More interesting, even aware-based Arduino boards successfully compiles and accepts this library. The only limitation, it's about 2 kilobytes of memory, so size of both vocabulary and data memory must be decreased significantly. So it's almost not usable. But now I can connect any library for from the Arduino store, wrap it by FORTH word, and run from the console. That's easy. What about more serious PC applications? how many libraries we need to add, how we will debug it, how we will support it. Finally, we are going to write a copy of existing code base. We need to re-implement everything in FORTH. So we can write a small FORTH core, of course, it's not a problem. We can write a library, what we had patents to write. But there are many libraries with Wi-Fi, with Bluetooth, with networking, with mathematics and graphic, and so on, so on, so on. What about more interesting activity? This re-implementing of existing features looks boring. It's Peter by Larkon la mass fair is boring. We don't need to copy existing code base. We need to switch to a project. So this small dragon is evolving, and we can add our tiny FORTH virtual machine. Oh, oops. We can add our FORTH virtual machine as a module, as a library, to a large existing, maybe C++ or Python or Java-based project, and use its libraries, add a FORTH console, as we creating a graphical user interface. Run scripts and rule the entire collection of our library written for another language. Okay, just an example coming from Qt. It's pie chart customization example. I can show how it looks like, and I can show what I add to it. Okay, it's just an example. It's just an example. Adding line to enter our FORTH text, adding button, and adding a code to initialize vocabulary, and adding a code to send our strings to connected FORTH machine. The only thing, I will explain it later. I can run it. Okay, 2 widgets are added comparing to initial example code. We can switching between color terms. I can enter number, and this number will be used as an index of this list. I can switch terms of this pie chart by executing FORTH strings. So I can rule this graphical user interface. Why it's so simple? Why I can't, for example, type something like this? It's interesting. It's interesting. Because when we're adding our FORTH library, we need to connect our FORTH word to some kind of actions in our main program. But for example, how can I change the caption of my button? I need execute button, set caption. But I have no pointer to execute button. I have no pointers to my main program widgets at this time. Okay, later in Qt CPP file, I will write push button pointer is execute button. This is new Q push button. The pointer will will be appeared and executed and initialized only at this time, at a runtime. I cannot define a pointer to an object which is not exist in compile time. That's a problem. That's a problem. Okay. So we can split Fort virtual machine and the main application engine. I can tell something about evolution of Windows graphical user interface application. First generation was based on this loop with get message, translate message, and dispatch message. I think everyone who wrote Windows-based early stage application is familiar with syntax. So we need to write a function. It's our function to do something useful. We need to write a message generator, for example, button, that will generate a message with a specific ID to our main Windows loop. And we need to modify a window handler procedure by adding another message ID to process. So this is 3 pieces of code in different places of our software. It was not so convenient to use. So rapid application development, Delphi, C++ builder, the next generation of creating a graphical user interface application. We can place a widget and all code templates will be generated automatically. We just need to write a function to run inside button, press it. Okay, it's far more easy. Now we can build another level of this hierarchy. We can define a set of widgets in inactive state. So we can create and define all of this. Widgets are supported by the application engine. It's not our Fort code. It's just C++ or Qt or maybe Lazarus Object Pascal. And all of these are ready to run something, some procedure, some code. And this some code is a Fort string passed to a Fort virtual machine connected to our application. This is a very simple template. Starting window is empty, but there are many widgets are created already, but they are hide. For example, with button, we can do show, hide, set geometry, so coordinates and sizes. We can set caption, and we can, this is new, and this is different from Lazarus IDE. We can assign a string to run in connected Fort virtual machine. With another widget, we can also show, hide, etc., etc., etc. So, okay, I can show how it looks like. Oops, what's this? Okay, I can show. It's very easy. Okay, I can hide this. I can hide this. I can show button. This is my button. I can define new button geometry just in interactive mode. I can define new caption for this button. So I can create everything in my graphical user interface from my FORT script. Okay, how it looks like from the programming point of view. This is main thread, our main application written in Object Pascal, Qt, Java, Python, maybe something else. We need to add console to pass strings to evaluate in our FORT machine. FORT virtual machine, it's a child thread created inside our main thread application. I created 4 threads for 4 different FORT virtual machine because 16 threads significantly load even my Intel i7 CPU. So it's 1 main thread and 4 child threads for independent FORT machines. So main application is written in our base language, most common for us, most effective for the main part of our tasks. Text console is used to pass strings to FORT VM, and FORT VM may pass a message with a custom format, placing in FIFO. And our main application with idle state will check the FIFO, this process messages, and send appropriate messages to all widgets it has. This will solve the problem of mutual visibility, because we need to add our FORT VM, but FORT VM have no information about widgets created later. So FORT VM just putting a message, it's a temporal state, so it's very abundant, it's no useless fields here. So it's index of virtual machine with putting a message, type of message, type of objects, so button or maybe progress bar, maybe label. It's index of these widgets in a widget collection, and many parameters. It was very simple. When I need another field, I just add it to this huge record, no matter. Okay, reading that data make us some problem, because FORT machine is simple passing message and continue to work. For example, if we need to read text field or read maybe checkbox state, no information will be passed to our FORT machine because our main engine is busy by some other task. It will write to our variable, to our data memory value, but later. So we need to provide thread synchronization. For example, VM flag to indicate VM is busy and still processing passed string, and flag to indicate graphical user interface is processing a request from a virtual machine to read some data from our placed widget. This looks quite easy. So we setting up this flag as a true. We are passing message to FIFO, and we are waiting for this flag to be cleared. It will be cleared when our main engine will place text data from a text field to an address. We send it. G address, it's just an address of our FORT byte array when we expect to read a text field from our widget. So all messages, all commands waiting for reading something from our widgets must be synchronized. It's small but very important note. how many widgets. I just place here a snippet of my code. So it's not 10 buttons, it's 1,000 buttons and 1,000 checkboxes. Of course, it's too high, but it's not an overloading of our operation system, because memory will be dispatched to our program only when we create and start to work with widgets. So we can use lists, progress bars, images, text fields, charts, line series, graphics, and so on, so on, so on. Okay, this is a very simple example from Rosetta code base, how to add two numbers. And all of these are here. It's not a console application. It's not a console application in Fort. Okay, 2, 3 plus. Yes, it's easy, but how we can explain? Okay, this console is indeed a Rosetta code example.
Ilya, we are passing 20 minutes now.
Just 3 more slides.
Okay, fantastic.
Just 3 or 4 more slides. So we can place and activate widgets. We can place labels on it, and we can write a text in Fort to execute when this button is pressed. So get integer for 0 text field, get integer from first text string, plus, and send it to label number 2 as an integer number. Okay, that's all. And what is how we can design our graphical user interface? More complex. We can add OpenGL libraries as well, and rule the OpenGL code the same manner as we can rule button and checkbox. So there is no code written in Fort. Fort is used only to push messages to FIFO, to rule main engine, where all needed actions are written in Object Pascal, for example. Some practical results, when I was started to work with MATLAB, I was needed to create this pretty looking graphics from its very familiar mathematics journal. And this is a snippet of my article published in May. When I tried to use MATLAB and our mathematics tools, I was very tired. So, okay, I know Fort and I can use it to create image and chart and line series. So this graphics was generated with my Fort. Okay, the last conclusions. Fort is not an opposite language, but it's a complementary technology for software designing. Strong features, scripting, so we can use it as a glueware. And very compact virtual machine core, so retargeting is quite easy. From PC to Arduino, and even for aware Arduino, but I don't want to use it this way. It's for Cortex, for example, with 10 kilobytes of memory. So existing disadvantage, we have very small code base. We have very small number of libraries implemented. This can be compensated by adding Fort VM into our application as a scripting engine ruling by the existing code from libraries. So when we writing everything in our base language, we need to recompile a large project every time. I showed you my Arduino. We spent about 10 seconds to recompile and load it, even if the project was quite small. We need to spend 10 seconds, 20 seconds, and maybe minutes to recompile, reload, and check how it works. And we need seconds to type something in the FORTH console. When we try to rewrite everything in FORTH, we need to do a lot of work to reproduce existing features and move it from base language to FORTH. We need to be something here. For example, FORTH wrappers for existing functions. So that's all. Now we are here, and I hope we're ready to fly. I hope we're ready to fly. It was the last part of Planet lectures, so I hope you enjoyed. Thank you. Questions?
Fantastic, Ilya. Excellent. Please unshare the screen.
Okay.
Great lesson. Fantastic. Guys, we move on. We are a bit delayed, and I have Dr. Ting, Bill Ragsdale, and Peter Jakacki. So if Dr. Ting is ready, he will present Java Force, a new version. Or Bill, or Peter, I don't know. Who of you?
I'm still trying to work something out here, so. So, Bill, or?
What should we do, Peter, for the next time, your presentation?
Yeah, I think probably next time I'll give a much better presentation. This time I have, I've worked out some bugs, but I still need to do more work on the. I would hope that to have a much better graphic interface to the Java Forth. Okay.
Okay, Dr. Ting.
Yeah.
Perfect. Well, Peter, your presentation will also not be ready for today. You mean?
Have we got another one yet? Bill, is he doing a presentation?
Yes, we have Bill.
Yeah, it's still a possibility I get this running because it's just a bit of a mystery to me at the moment what's going on. But so it could be up and going. So, but I will continue to keep working at it, and yeah. So that's
fantastic. So I present Bill Ragsdale. Don't fear with the deep stack. Bill,
right,
you're up.
gentlemen.
Okay, you're entering it.
Ready to go, gentlemen.
Go on, please.
Thank you for the opportunity to present. Bill Ragsdale here. There's been discussions circulating on the FORTH2020 website on locals, deep stacks, local variables, when to simplify, when to not. So I intend to address one of the components of that. Today, the basis of this presentation is going to be on implementation of matrices, matrix algebra, linear algebra, and FORTH. And as some background on that, to express a matrix, we need 4 levels of access. First, we need the memory address of the matrix itself, then the cell size that's used to store within the matrix, in my case, 8 bytes for floating point numbers. We need to know the overall matrix size, total number of rows and columns, and we need to know the offsets within the matrix to identify the cell or a range of cells. A fair number of parameters. And as an overview or as an element, if FORTH matrix addressing is 0-based, I tried to do a dual basing to be able to switch back and forth, and it got totally out of hand. So since do loops are zero-based, my fourth matrix work is zero-based. As we know, in conventional matrix arithmetic, the rows and columns are numbers starting at 1. So the realities of handling matrices are that they do require a large number of parameters. However, the parameters can be hidden at the top levels, at the user level, at the programming level, but they're expanded at the lower levels as you get down to the primitives. For example, to address one cell, you need 8 parameters. You need to know the address of the matrix, the cell size, the total number of rows and columns, and the rows to and the rows from. Total of 8 parameters. If we're doing arithmetic, where we're taking A plus B to C, it actually involves ultimately 24 parameters on the stack. There's no way to avoid it. One way or another, 24 parameters will be on the stack. Now this can be simplified down to 5 parameters per matrix, because for the visible side, all we're doing is the matrix address and then the row column numbers. But at the most extreme level, as we'll see, there could be as many as 15 visible parameters for arithmetic. Well, one alternative would be to use 15 variables, offload all those values into variables, address them by name. Another way is to use 15 locals. There's a variety of number of ways to do locals. Sometimes they're passed en masse in a block to the return stack and then given names. The way that I'm doing it is to use deep stack manipulation with a small number of low-level words. That is, the top-level words are simple. The low-level words become quite complex with deep stack usage. And I'll propose the use of deep stack words. More about that later on. Of course, the starting point. This shows in green the definition of a matrix. 3 by 3, 3 means it's 3 rows, 3 columns. The create left brace is the creation word, and it's creating the matrix A with a left brace. My convention is that every matrix ends with a left brace, with a left brace on the right side. So we've created a matrix A. We then use the word to fill it, the word to list it. In this case, the matrix is loaded. Each cell contains its row and column number. So the top left is 0, 0, row 0, column 0. The bottom right is 2, 2, row 2, column 2. This is just a handy way for testing. There are 3 matrices for testing conditions. This will be used uniformly through this talk. We have A and B, which both are initialized with this row and column values. And then matrix C is the result, and it starts out always as 0. So here's a simple addition. Couldn't be simpler than this. We're going to add all the elements of 2 matrices. We declare at the top left A, B, and C, and then with the right brace plus, add them together. And we see at the right, we're taking the A matrix at the top, the B matrix in the middle, and green at the bottom is the sum, the total of the 2. I will also make a note that all math operations are cell by cell. There is also a matrix multiply and matrix divide, but these are cell by cell. This is a little more involved. We're now going to add specific rows. So again, we have our A, B, C. The number 1 at the top left, 1 says we are going to operate on row number 1. And then R plus is a simple mnemonic reminder that we're going to add 1 row. So we see on the right at the top, we're taking the middle row, 10, 11, and 12. In the middle matrix B, we're taking the row 1, 10, 11, and 12, add the 2 together. At the bottom, we get 20, 22, 24, the total by row. The definition of this R plus, you see, now we're expanding the parameters to get the full suite that's necessary. And we pass that to a word sub plus. This is doing a submatrix addition. In this case, it's isolating those particular rows, adding together. So the user sees the top left, the simple form. Now let's add independent rows. In this case, we're going to take from the top left, matrix A, we're going to take row 0. Matrix B, we're going to take row 1. Matrix C, we're going to have the result go into 2. In this case, the definition is RRR plus. This reminds us that we need 3 row parameters in our input. At the right, we see the result, the green top row at the top, the green middle row in the middle, and the result goes into the bottom, 10, 11, and 14. And the definition of RRR plus, again, this is not visible to the user. This is done at the system level where we're expanding the parameters to specify the row information. The same thing applies to columns. In this case, we're doing 1 column, ABC1 column plus, adds columns together. And we see on the right, we're taking the center column, the top, middle, into the bottom. Now we're adding independent columns. In this case, we start with column A, a 0 column. Matrix B is row 1, column 1, and matrix C is column 2. And again, CCC plus tells us we need 3 column parameters. And notice how they're added together, A, B, and C on the right. Another variation is this adding over a single cell. In this case, we're taking a single uniform cell in all 3 matrices. So at the top left, we have ABC11, which means row 1, column 1, and the RC plus indicates we need to specify a row and a column. We always have the mnemonic built into the operator name telling us the parameters that are required. And we see at the right, we're taking that center green 11. In the middle, we're taking the center green 11, we're adding together, and the result goes into at the bottom, the 22. In this case, the expansion is fairly simple. We see that of the definition of RC plus. Now, this is the most complex of the bunch. This is adding arbitrary submatrices. However, the submatrices are in common. That is, they match matrix to matrix. So we're taking, again, 3 matrices, A, B, C. In this case, the submatrices are row 1 to row 2, and then column 1 to column 2. So we're doing a submatrix that is a 2x2 matrix. And we see on the right how, again, we're pulling out components from the A, component from the B, place in the C. And again, finally, the most complicated. In this case, we are doing a totally independent submatrix. So from the top matrix A, we're doing row 0 to 1, column 0 to 1. From the B matrix, we're taking row 1 to column 1, column 2, and the result is going into the C matrix at row 1 to row 2, column 1 to column 2. Again, the highlight in green shows us the information copied from A, B, and result into C. In this case, we're actually having all 15 parameters are expressed. And again, this is fairly unusual because usually in this sort of manipulation, we're doing things very routinely, rows and columns or cells. Now here's part of the payoff. I've specified now a total of 4 math operators: add, subtract, element multiply, and element divide. The geometries allow us to operate on a matrix. At the top, at the left, we see matrix, a common row, independent rows, common column, independent columns, single cell, common cell, or independent subcells. So there are 32 combinations, 32 operators. And miraculously, these all are derived by utilizing one master fourth common root word, which is read at the bottom, which is left paren, right brace, sub X, right paren. I'll refer to this in the future just as sub X. Here's a pseudocode for sub X. Rather what we expect. First, we check the input ranges of our parameters. Then we copy C to transient. It is possible that we could be operating on the same matrix. We could be going A plus A result to A. So therefore, we want to have our results going into an isolated matrix because we do not want to modify our inputs as the process occurs. So we copy the C resultant matrix to a transient matrix, set up the do loops over rows and columns. First, we retrieve a cell from A, retrieve a cell from B. We do the math operation, add, subtract, multiply, divide, and we store the result in the proper cell in transient. And notice, in this situation, all three cells can be independent. They do not have to be uniform. We loop over all the columns, we loop over all the rows, and then finally we copy transient back to C, and we clean up the data stack and we're done. The results in C. Here's the D chart of what's going on. It says in graphically what we just said a moment ago in words. Top left, we check the ranges. We copy C to transient. We set up the loops. In the middle, we go over the rows. We go over the columns. Then cell by cell, we take a cell from A. We take a cell from B. We perform the operation, add, subtract, multiply, divide. We place the result in a transient cell and go to the next column. When the columns have been all passed over, we go to the next row. When the rows are exhausted, we come back to the bottom left. Here we're copying transient back to C, and we drop 11 parameters. Now, this is the definition of sub X, and here's where we go deep stack. The input parameters for sub X are given at the top. For the A matrix, we need 2 rows, 2 columns. For B, we need 2 rows, 2 columns. For C, we need 2 rows, 2 columns. And the tick F plus passes the arithmetic operator to sub X. So in this case, we have 16 parameters input to sub X. The deep stack manipulation, I'm using pick and roll. So when we, at this first line of sub X, we see 14 pick, 11 pick, 11 pick, 8 pick, output. Those values are all duplicated and they're passed to a word called 3 range valid, which does a range check. The same text is repeated. The third row down is setting up the transient matrix. And then all those picks and rolls in the middle are setting up our do loops. Finally, in blue, we see where the work is done. The top blue row is 13 pick J plus 3 pick I plus, and then a matrix fetch. So in this case, we're fetching from matrix A. The second blue line, we're fetching from matrix B. You'll see there's the execute in green. So this is now doing the math operation, add, subtract, multiply, divide. And then finally, the bottom blue row is placing it back into transient. We go over the loops, we clean up transient, and at the very bottom, we're dropping 11 parameters. There's a 4 drop, 4 drop, and 3 drop. So notice, this is where the work is done. And this took me about 6 hours to develop. I had to redesign it 3 or 4 times. And again, a total of about 6 hours. But once it's done, it's done. And also, you can then, from then on, you can just ignore all those picks and rolls because they are never visible to the user. Let's talk about speed of execution. The execution time of this, adding 2 matrices together, is 16 microseconds. So that means if we're doing this over 1,000 matrices, it time lapses 16 milliseconds. So I see no speed penalty in this kind of work. And in fact, the streamlining of using pick and roll, leaving everything on the stack, actually enhances the speed. I make an estimate that at the same time period, we could do an addition of a 95 matrix by 95. Again, that would take about 16 milliseconds. So as an alternative, we could consider using local variables or offloading the variables. When I hit this point, the little light bulb went off over my head and said, well, why don't I make up stack words that are kind of like locals? We will just give the stack positions names, and they could be girlfriends' names, they could be states' names, they could be alphabetic, or I'm just doing pretty simple. When I want a 2-pick, I'm just going to name it 2-pick. When I want a 2-roll, I'm just going to name it 2-roll. Now, we will see on the next slide, this simplifies the expression, but I am not sure that we've made a real improvement. The code is just as clear, but the space taken by adding these words is roughly offset by the space we save by not using literals in the definitions. So I look at this right now as the jury is out. It may be handy to use these deep stack operators. Possibly just using the classical form would do. Here's the classical form. We see it's 14-pick, 14-pick, and so on. When we use these operators, notice all we've done is taken the space out. So under the green sub X, we have 14-pick, 14-pick, 11-pick, 11-pick, 8-pick, 8-pick. These are just words. Now, all they do is expand into the number 14 and the word pick. This decreases execution time or increases execution time slightly. And in some ways, it may make the code a little bit more readable. So we're going to summarize what we've seen. First is that the routine manipulations and math are straightforward and brief. Listing, adding, initializing, adding, multiplying, subtracting are very straightforward, take a very minimal number of parameters. If we get deep into complexity, we could need as many as 15 input parameters. Now, one alternative would be, as I've mentioned, is to unload those parameters into variables or values, and then reload them when they're necessary. But why do we offload parameters into variables and then we pull them back later on? So we've made two operations that are unnecessary when the parameter was on the stack to begin with. And also, the major effort of creating these new complex words saves specific coding and space. In other words, by combining those 32 words into one, I put all my effort into one word, and the definitions of those other 32 words are very straightforward, very testable, very reliable. Here's a very rough comparison. In MATLAB and Octave, which are both matrix languages, they use an elaborate syntax. The variable expression is simply a name, but all of the rows, columns, and precedence is done in a variety of syntax of square brackets, round brackets, braces, colons, and words. And I've made up a hypothetical example here of what it could look like. When I reach an example like that, I throw my hands up because the documents do not tell me the parsing order, and they do not tell me the priority of which element executes first. In my approach on matrix forth, every word is separate, simple. Every operation has its own word, and the syntax is specified by the word name, not by, let's see, the semantics is given by the word name, and the syntax is given by the parameters. So we've isolated syntax and the syntax and semantics. So in matrix forth, we've taken this complex syntax with many functions. Each function has a crystal clear syntax, and you can add your own. And matrix becomes extremely easy. So I'd like to thank the late Dr. Julian Noble for the key concepts of matrix structure and its parameter use. The book Scientific Forth is available under limited conditions. The copies on the internet are expensive, but there is a downloadable copy if you search far enough on GitHub. I'd like to thank Andrew McEwen and Tom Zimmer, who created Win32 Forth, and the European team that updated it in the early 2000s. I posted this on my GitHub site. Look for it under matrix word set. This gives the full matrix language implementation. And then finally, I published a book on Win32 Forth. So it's also published at Bill Ragsdale at GitHub. So thank you all for your rapt attention. Are there any questions?
Yeah, I have a couple of questions. This is really cool. So at work, they're doing inverse kinematics, and they're using matrix math with trig. Can you bring up your screen where you for local variables, where you had to find one, you know, the different picks? So let me just ask you, why didn't you use a more higher level name? In other words, you know, some matrix name, like, you know, matrix A, B, or C, or in other words, instead of making it, you know, like, let's see, where is it? Instead of shortening the word, like taking out the space, why didn't you choose a word that's more descriptive, I guess? When you were talking about local variables?
Yeah, for some reason, I have trouble getting, see if I can get to that.
Are you referring to the npick, like 3-pick?
Exactly.
Yes. Yeah, I thought the same thing.
There we go.
That's it, isn't it? Yeah.
Well, let's open it up. I guess I might say this is quick and obvious, because all I'm doing is identifying those parameters by their pick number. However, at various times, the parameters are not the same. In other words, we do not always have a uniform set of 15 variables across the stack. So if I was to give them meaningful names, I would have to create synonyms for this. And when a given variable was at the 6th position, I would have to give it one name for one operation and one name for another operation. So instead of these 26 words, I would, you know, they become application specific. Still can be done. You can synonym any of these words with an application specific word. Is that reasonable?
Yeah, okay, I get it. So basically what that tells me is locals don't buy you anything with this application.
I'm not so bold as to make that statement because I've never used locals, so I won't comment.
Having
in the system I used in 132.4, locals are present. However, to the best of my knowledge, they are not documented. So I've got to go read the source code to figure out how they work. And it's pretty involved.
Thank you. That's very, very interesting.
I can't comment on would locals be faster or simpler, since I haven't used them.
Locals are not faster. It depends on the force you're using, but locals are super important in math applications because when you write an algorithm or you write any equation, you can use mathematical terms, and your code is more readable. This is the importance of locals. And if you read the scientific library from Carter, you will see the first implementation he makes is locals. If not, the code becomes absolutely impossible to understand.
Well, what I found in the work I'm doing, almost always I am using matrix expressions like the green at the top left. We're just saying, take 3 matrices and then take a single cell, 1, 1, add them together. And in this case, I see locals buy you nothing because you are having 2 numbers on the stack which represent the row and column. Why would I offload those into locals to give them a name to say, then add the 2 names together?
Well, what you did was you created a matrix math, a new language. And that's what I want to really, you know, hit home with. You use Forth to create a new language. If you need something in Forth, you know, I love that part.
I agree completely. Isn't it the case whenever we solve an application, we're writing a new language that's application based? That's forth programming. You're writing an application-based sub-language when you program. All right, we probably better wrap up. Let's turn back to the group, and thanks so much for your rapt attention.
Fantastic, Bill. Fantastic. Excellent.
Well, Peter, I might have something I can show you. I've sorted out the little funny things that were happening. Now, I'm going to share the screen off my monitor over here. So not off this Zoom camera here. So I'll just share that. So I'll probably need. I'll just check where I am at the moment. Okay, participants. Let's just check what's going on. Okay, so that Peter Bruno one, yeah. So that one there, I'll just need to share a screen. And what I'd like to do is just show an old application I had. It was for a friend of a friend, and he had a factory making wall panels for roofs and buildings with foam injection, and he would make transportable factories where we had have the hydraulic frames and the pump equipment and everything all set up so that it could all be transported and flown out and so on, so they could make wall panels. And so initially, with this application here, I'll just share the screen here on this document here, which will show a little bit more before we get there. Now, so right now, can I share off my Peter Bruno account there that I've got up on the other one there, Peter? Just let's see if I've got any. Oh, yes, I can. Yes, sorry, I can. Yes. So share. And over here, I have this one here. So don't need to share any sound there, so that's okay. So now I'll just make sure I can see all that coming up. Yes, they're good. So this is a Google document you can see up here. And what it is, the Google document is the code, the pictures, the description, everything all in one. And my initial projects that I did with Tachyon, I wanted to be able to help others see how the code related to the project. And so I would create them in a Google Doc. The interesting thing is that when you come along and you select everything in there and copy that, you can paste it, but it only pastes the text. And of course, I'd have block comments up around there as well. Like you can just see there on the document there, you can just see where the cursor is, there's a start of a block comment and right down the end of the table there and so on. But the graphics and everything else were totally ignored. So this is a really cool way because I could create projects and put a whole heap of information in. As you can see, this Google document, it just describes a little bit about the application that I have. And it's, you noticed up on here, right where, I'll just make sure my cursor's up there properly. Yes, up over here, you see this little box that's on top of this, this bit of equipment over here on the left. That was the original counter unit that they had. It was totally useless. It was very awkward, big, heavy box. And the friend of the friend said, look, I know you can do this stuff. Can you do something for this where they can automate it a bit better? And so I came up basically with a little bit of hardware. It didn't have to do much. It really only had to monitor a couple of encoder inputs. In fact, it was only a simple encoder input, but I improved that, and a valve pressure, and basically, and also, oh yeah, just indicate to the operator, they had all these different frame numbers. So you can see a frame on the right-hand side over here. This hydraulic frame, they call these machines or machine frames, and they have a whole, whole stack of them, and they set them all up, and each one is set up differently. So what happens, I'll just turn my camera around. Well, in fact, I might be able to just turn my camera around at my setup at the moment so you can see what's going on. So I'll just change this over. Here we go. This one here. Okay, so hopefully I've got that set up right. But going in there now, I'm not even quite sure. Yes, I'm pointing out, yes, and I can't zoom up on it, so I'm going to have to just take it up here. So you can see I have a monitor screen here. It's only a small screen, but normally I have all these large screens all around the factory, as many as required. There's a small little module that plugs it straight into the VGA socket on the back of the monitor vertically. So right in the very back of it, just plugs straight in. And on there, we have connections for power, 24-volt power, and RS485, and a keypad. And so what happens is these can be positioned around the factory. The operators, when we look back at that document there, the operators are far away, but they can still see those monitors and what's happening. At the moment, I have a screen up here. I'll move the document along. I'll tell you what, I'll just do this a little bit, see if we can see it from there. We can see enough there. We can see the control board, the keypad, and the control board down here. I'll give you a bit more light there too, just so that you can see all that. And there's not much to the board. It's basically a little propeller chip underneath that board. I've got another board over here. You'll see this one a bit better over here. If I just make sure I'm, where am I? It's okay. I'm trying to see where I am on the camera here, so just bear with me for a moment. Okay. All right, just come back. Yes, there we are. Okay. All right. So we've got one of these boards here. It's got a little propeller chip in it. I have my Tachyon force loaded on that, and then I have a small I/O module. And there's also this is an older board, and it also has RS485. So on there, just underneath that sticker there, and so that's all that really does. It doesn't do much. A little MOSFET driver drives a solenoid, 24-volt solenoid. And what happens is that, looking back at that document.
Hey, Peter, it would be better if you stopped sharing your screen so we can have a bigger picture.
Okay. Well, that's good. Look, I'll do that. So I'll just stop that share. I can pause it, can't I? Will that do that? Does that help? No. Okay. Resume share. Stop share. Okay. All right. All right. So you can get the bigger picture there. All right. I can see that too.
Yeah,
so,
right, great.
Now, yep. All right. So we can. This is a screen that they see. There's also one that's more convenient at eye level that they have the keypad for, etc. And really, that keypad's normally wrapped up in plastic because they've got all these, all that foam stuff and everything else all over the place. And so they come around, looking back at that document back over here. What we see is, I'll pull this out of here. What we see in there, I'll show you now. So this frame here, they have the gun that goes in there, and as soon as they press the trigger on there, the pressure drops. Then this thing starts proportioning and mixing and pumping and counting the strokes that are coming through. So it's fairly simple, but the thing is that what I like, it's all in a Google Doc, everything, the code, the lot, all the documentation, and then we have the screen up there, and then over here, let's just try this out. What we do is we do a setup. I forget how all this stuff works, mind you, so bear with me. And normally they set it up with different machine frames that they have in the factory, whatever they do. And I'm just taking a guess at this, what it is, number 12. Skip a couple, make it nice and easy for editing. They can just hit the enter key over here. Give this one 8, count of 8, etc. Put this one down for 10 and skip a couple, and let's go right down to 14, and let's put a count of 16 in there. Okay, all right, so 16. What I can do is the operator normally comes along, says, okay, this is all set up for production run. Each of those frames that we saw just before in here, they're all numbered, and they've got a very long hose and everything. So they're looking at the displays. There's a pump unit over there. Over here, it's a pump unit right there, and the proportioner and everything else. And so as soon as they press, well, what happens is they tell it to run first. I'll just go through the operation. I'm going to show you the code as well as I do this, but hit the run key. As soon as you hit the run key, up it comes. It says you're supposed to be on machine number 1. It's going for a count of 12. You got 0 strokes. It's all zeroed out at the moment. Low pressure, and I can't remember what I've got over here. Okay, but all that's set up, and so essentially what happens. I don't have the encoder set up at the moment, but it's running off a magnet that goes off the actual the arm on the pump that goes up and down. And just to make sure it counts accurately, I have 2 encoders. So basically, it'll latch in software, and so that way it won't get those funny, debounce type pulses that Christian knows about, etc. So we just get nice, clean pulses out of it. So let's put a pulse in. I'm going to press a button on here because I don't have the encoder handy. So I'll just use one of these ones here. And what I have to do is I have to do an A-B type. I hit A again, won't do anything, but I hit B, it'll count that. And so these are like half strokes, and it'll just go up and down, up and down. We can just see this in operation at the moment, and we'll come back to the code in just a moment. There it goes. It's hold, and we have to release the gun, seal it up, go up to the next machine number 6. Once we're ready, it says, yes, you can go for it. And then they press the trigger, the pressure normally drops. It's much, well, it's not exciting at all, but it's much more interesting when it's in real operation. I have videos of that too. So we see that going through that there, and we've done that. The next machine to do is machine 7, and we're all ready, and it's got a count of 10. And that's good for the operator. They can check, see what's going on. Notice the graphics aren't real good because it's just, but the main thing is you can see it from a distance. So there we go. And then I think the last one I had 16 on it. There it is. So 16. So I'm just going to go through that one there, just count through them. Let's just run through this quickly and get this over and done with. A, B, A, B, A, B. And it's pumping up and down. It's 2000 PSI. You don't ever want to have an accident with this one. And there it's all done. Okay. Now there's a whole heap of other functions in there for storing and recording and logging information. But what we have there is basically what the operator sees. And it's nice and simple. As you can see, there's hardly any hardware. And because I've done the little propeller chip, and I'll put that on the 485 and spread it around the factory floor, then we can have keypads plugged into it. And it only requires a 4-core phone cable, essentially. You can go use anything you like, but I've just used phone cable, 4-core, running it around the factory floor. And the 24 volts powers that VGA module as well at the same time. So it powers that. And the display, of course, has to have its own power, but it could be powered from the 24 volt supply if I wanted to. A lot of these monitors are 12 volt. And then what happens is coming back, I'll share this document again. I'll switch back again.
Yeah, I can.
20 minutes.
Yep. So
I can. Yeah, I can.
Yeah. Share this document. Okay, here we go. Sharing. Now, just through this document here, I put in some extra information just for the fourth group here, describing the operation of it as such. Over here, what the control unit does, how they're all mounted, a couple of pictures of that, very handy for reference. Here's a block diagram down here. I'll move that up. Yeah. And we can see that. You can see that? Yes. So over here.
Are we seeing Peter Bruno's screen?
Yep, you should be seeing that screen. Does it come up when it's sharing like that?
We're seeing a fourth users group window.
Okay, that's my fault then. I thought I picked up the right one, so I'll just share share the screen here.
You got it.
Okay, back again. I see, yeah, here it is. It's this one over here. Okay, so that's the correct one now, isn't it? Yeah. All right, yeah, it looks like it's right now, yes. So,
Yes.
So over here in the document, the Google document, I have a block diagram showing the keypad layout, just the very basic connections on here. And of course, the actual unit itself, the front of the casing, etc. And there's nothing much to it. Here's a few connections on here that I like to have handy just to remind myself what's connected up to it, what isn't, on the schematic. And then down here, you can see some more code. Dummy operations there, but over here, application variables and constants, where I just define variables as longs or words, or 16-bit words or 8-bit bytes. And then here's some software timers that are dynamically created in here. And in Tachyon, I have one of the cogs, one of the cores, running just running a background task and maintaining all these dynamically linked timers. So I can just create them when I need to. And first off, all I do is I create a double, so what's that, 8 bytes. Each time is 8 bytes, just creates a structure of 8 bytes. Doesn't do anything until I actually load that up later on. I'll show you where that's working later on. Now, I'll keep this camera on the screen here too, if that helps at all. But over here I have, as you know, fourth, we've got to go right down to the very end. So let's go down right to the very end. Let's have a little look at this. And over here, this is the main task over here that's running EPC. And essentially all I'm doing is I'm initializing a stack, any PCB type hardware things. There's lights and different things on the front of this, by the way. And then I tell it just to run the EPC task. So initially when it first starts up, let's have a little look at that. We can see the code over here. It says, well, initialize the display. This is my my standard I use, the exclamation mark there in front for initialization, or store if it's after the word. And just go through and do a lead test. We want to make sure the LEDs look right. And then that's fairly straightforward. There's a couple of blinking patterns there, and individual patterns over here. And then I can position on the screen and print a little message there for 1 second, and then paint up the screen up here with different regions, paint it up, and then just pass that message over. Let's have a look at that. I'll turn off the share for the moment and come back, and I'll just power this unit back up again. So let's have a little look at it. Rather than power it up, I'll just tell it to reset, shall I? So tell it to reset, and what happens? Okay, that's the internal firmware. There it goes. That's started up. Over here, if we look down at this unit over here, we have some LEDs on the front panel, which are just hooked up by a shift register. So we'll reset that again, and let's see that go as well. What happens there? So there's the patterns, and then individual patterns we go through, and you can see that flickering away there just to check the LEDs. Back on the terminal screen, back over the terminal screen. Okay, if you can see that, hopefully I might even share the terminal screen. That might make it a tiny bit easier, and then you can just see what I'm doing on the terminal screen as well. So let's share that now. Share. Okay, here we go. Sharing the terminal screen. So we can see that. You can see that clearly. And so at the moment, the console is just being used for system messages. And if I escape out of that, I come back to fourth console. So I'm not trying to operate the fourth programming environment and the system at the same time. And so this is just the word list that's in here. What I'm going to do now is I'm going to tell it to I'm going to try something. I'll see if this works. Come on. Yes, something just did work. I'm not quite sure what happened just then, but just printed an OK up over here. And I have different regions, etc. on there. So I should be able to clear the screen. And I cleared the screen, but the regions, the tile regions are still painted up on there. And of course I can initialize the display completely. Let's just try that. This is an older version of software on this unit because I had some problems before, so slightly different. But that's just initializing it. The internal message on the Pixie unit itself is coming up, and so that's just coming up. And I talk to it in RS485. It's a nice, simple network. When it wants to read the keypad, it just simply sends an inquiry command through to these units, and if it has anything, it will send it. So I can just read it. So nothing complicated at all. And so if I have a quick look at some of this code here, if I change the screen now, I can tell it to just press the stop button, for instance. What happens when I press the stop button? That's exactly what happens. And so that's nice and simple. I'm just trying to think how else I can sort of demonstrate this with the current setup. But next time, maybe I'll do a bit better again. But I'll stop sharing that screen so you can come back to the camera view. And just looking at the screen there. So you can see the system is quite simple in terms of hardware, quite flexible. It does the job, and there's not a lot of code to it. I think there's, if I look at all that code there, in fact, I probably have to put, there's about 4K code basically when it compiles anyway. So when that goes in, that's 4K code, and the VGA part of it is actually on that other little module, so it doesn't have to worry about trying to run a VGA signal, 50 meters or so across a factory floor, and that makes it a lot easier to do that. So that's a nice, simple solution. I could probably show you a bit more of what I do for 485. But as I said, the 485 is nice and simple. I just send out a lot of commands most of the time, and then when I want to read a keypad, I'm not even trying to address any particular station. I'm just saying, do any of you guys have anything to give me? Now, I don't think it's ever going to happen that they're going to be using multiple keypads at the same time. So essentially the one that has any information just sends it back straight away. I'll have a look at this on the document. I forgot to share this again. Share the screen. I'll come back to that. Share screen back to the correct one. Okay, make sure that's up. There we go. And that's up now, isn't it? Okay, very good. All right. So now that's up here, you'll see that here's one here that just checks the keypad function over here. And I also have a keyboard layout up here, very handy. We can't normally do this sort of thing just in a normal, text document, but in Forth, we can just copy and paste. This is great. So check keypad function will go through, read the keypad. Let's have a little look at that function there, the keypad fetch function, which is, I'm going to have to look for it now. Okay, here we go. Over here. Nope. I don't think that's the right one. Obviously, I've got some mistake in here somewhere. I'm calling, I have the same name. Okay, where are we? Just bear with me for a moment. Okay, here we go. Right up here. Let's see if we make this a bit larger. In fact, I might even change that size of it altogether to 200%. And over here, so keypad function just sends an inquiry command out over the 485 line and gets a response back. That's it. It's so simple, and it's so easy to test as well. And from there, I also have anything to do with the display, colors, etc., functions, and painting those areas, etc., on the screen. It's a very low resolution screen, really, but it's effective for what it is. And then I also emulate some LEDs, etc., down the bottom, so they're virtual LEDs. I don't know this. I don't know how much simpler this application could be, but there's a couple of little things in it, of course, and the main thing is that, as I said, it's very easy to maintain. I've been out there on site, and I've just been able to go onto my phone or anything else, call up the Google document, copy it, paste it through the phone itself, because I have a little Bluetooth interface for serial interface that I plug into these units when I don't have that particular serial comms in there, and so I can just communicate with it over the phone and monitor what's going on and update the software. That's basically it. You know, it's not quite everything I wanted to show. I really wanted to have it all in action, but this is probably one of the simplest mechanisms. Not that I even had a real mechanism hooked up. I do actually have a little motor hooked up. That's about it on there. Let's just stop that share. This is supposed to be the valve. Would you believe that? Over there, I've just hooked up a 12-volt motor, so that essentially what I can do is, if I go back to the console, I can say, turn on that valve. Did it come on? No, it didn't. I don't know why not. Oh well, I've done something to it anyway now, but it was hooked. Oh yes, I know what's happened. I've lost my power for it. That's why. Let's get some power on there. Let's get that one hooked up. You don't need huge MOSFETs, you know, depending what you're doing. As you can see, that tiny little package that I have there is a dual MOSFET, and it can handle 6 amps easily. You know, you're just turning loads on and off. Let's see if I can get this back up here now. Okay, I've got power on there now, and so I should be able to turn on that valve. So you can hear that running there now. MOSFET's not having any problem handling that, so of course I should be able to control the speed of it, but that's a motor and a valve I normally just want on and off. And hardware-wise, I think I pointed this out to you before, but let's get a pen here so I can show you where this is on here. Over here, I'll get this light set up right. Over here, and I can show you that this little tiny chip here, right there, I'm pointing to now, that little SOIC 8 pin is a dual MOSFET. So yes, you don't need heat sinks, you don't need TO220 packs, and things can be a lot simpler. And I've just done that with a propeller. So I'll just switch back over here to my camera back over, just a sec. All right, guys, that's basically it. Any questions? Sorry
Peter,
about the delay.
I have a question for you. So, you know, you have a master fourth controller, and then you have all these slaves running around the factory, right? So, did you implement where you could like put in the slave number, and now you're talking to the slave, and you can download code and interactively debug the slave on the network?
Hey, listen, have you seen my YouTube video with these particular little these little boards here? These ones, have you seen those boards at all? There were 40 of them in a 3-phase regulator, 1500 kVA 3-phase regulator, using these 1000 amp type SCRs, and there's 40 of them in there. And what I did was, there's a little propeller chip with forth running on it, RS485, and isolation, dual isolation, analog measurement, trigger control, etc. And so it was made so that this could just plug straight into the SCR. There's no wires going anywhere else, and there was just one multi-drop cable. Now, I think I demonstrated that on YouTube. I'll have to just post a link through, and I could chat with anyone. They all had individual addresses. I could address them globally, send them the same program, give them the same command, give all these ones in a group the same command. But if I wanted to chat two-way, I could do it over 485, and I have what I call a ping pong network where I could just send one character, and if it was selected, it would send one character back. If it had nothing, it would still send a null character back. And so I could emulate full duplex terminal as if I was connected to it serially, do everything I could, and it was hooked up in such a way that it was actually built into the serial receive routines. If I plugged in serially into it directly into the module here, onto the little header, it was exactly the same if I did over 485. So it made it really great for development. I'll have to demonstrate that one time, won't I?
Yes, that's very cool. And that shows, because you can redirect basically the terminal interface to Forth like that. It's very easy to do that. This kind of thing comes almost free with Forth.
Yes, and and I mentioned before that this is a three-phase. So your 415 volts, three-phase regulator, very dangerous. Just the control cables for it were this thick. What I would do is I'd have my laptop connected via Bluetooth, so I was at a safe distance. One time I did something did the wrong thing, and that whole building filled up with black smoke because those cables were just starting to melt just from the current. So if I had a lot of power on there would be a huge explosion. So yes, it was great to be able to diagnose it all and everything at a distance, I can tell you that. And so that 485, I've implemented all kinds of networks with 485. Industrial control, you have simple things like Modbus, but I've implemented other types of networks that are more suited for, like even in fire handling, high-rise buildings, etc., and lift displays. I've done a whole heap of things in Forth, and just used custom type protocols to suit the application.
Christian wanted to debug your 1000 amps tires.
Yeah, that was a control current, by the way. These are only for the control windings. They're not the actual load current itself. And it's just we had a huge generator brought in for testing the unit, and it was, but basically it's a great big 18-wheeler, and then it's got another great big fuel tanker and everything else to go with it. And that was a 3000 kVA unit, and because we didn't have the safeties in place, that just sat there, and it cost a lot of money. I was never going to hook it all up. That's a long story. I'll have to tell you about that one another day. But technology-wise, this is really cool because we could just plug it into each one. The original unit was a Chinese-made unit. It never worked, and it was a huge board, another huge board, and cables going everywhere. And here, I just simplified it because there's just one tiny little 10-way ribbon, and I would just plug it in, 10-way ribbon in, 10-way ribbon out, daisy chained it all along. It was a simple multi-drop, and yet I could talk to them individually or, as a group or anything else I like. So very good for debugging. Great fun.
We use this kind of star systems, from NMY, the 68H11. They came with ERAS 422 and ERAS 485, and it was very, very easy to use with force.
Mm. Yes. The so, you know, as I said, networking can be something very simple. I've implemented networks where essentially this one here was basically if I send out an address character and it matches, so this unit to be address number 5, for instance, and I send out address 5, you're selected, it responds, it says, yes, I'm here, I'm number 5, it remains selected. So it's like dialing something up. And because it's the only one selected, it could also communicate back at the same time. So that was a very convenient one because, and also with the ping pong type traffic, I was able to really make it a virtual full duplex connection. And of course that was just running at 2 megabaud, you know, it was just so I had no trouble with, you know, serial consoles talking to it over that. Yeah. And the other thing too is because 485 networks suffer a lot from collisions or timeouts. You know, what happens here and what happens there in different areas. And, you know, you can have multi-master networks or master-slave. And this just made it super simple, just like Forth, you know, just works.
Well, next in the we don't have any more presenters in a moment, but I have some people who are new to the group. One is Rick Carlino. I don't know if Rick, if you are here.
Can't see Rick on there.
Yeah. But we have Jan Langevart from Denmark, who is for first time in the Zoom, I think.
Yes, hello.
Hello, Jan.
Can you hear me?
Yeah.
You hear me?
Yeah, yes, perfect.
We can hear you.
Okay, great. Thank you. It's wonderful meeting all of the guys here. I'm a happy amateur, as you know, but the project I'm running on now is trying to implement a Motorola M6800 chip into an ESP32, and it's to end up in this little creature. I hope you can see it. This is a homemade Altair 680. I'm afraid the picture is not that good, but you see how I have built the box already, so it's just needing the CPU, and that is to end up in an ESP32. And this one has the serial lines, the RAM and the ROM and everything, so it should do the job very well. And the Forth is very, very good for implementing another processor. It's not hard work. The only problem is implementing all the condition codes. It's very, very tricky, but the condition codes do in the Motorola chip. And the description for Motorola is not very precise. But I have tried to implement a Motorola 6800 chip before. I did it in Delphi on a Windows PC. So that's the situation now, and it's wonderful to see that Zoom is working, because I've just moved to the summer house and I only have a 6 megabit connection, but no troubles at all. So when my project is completed, I can happily show you when the Motorola is up and running in an ESP chip. Well, that's all for now. Any questions?
Of course. Yeah. Fantastic, Jan. I like you. I love so much you are in the group and you participate with the ESP32 Force. I think Brad is listening to this. Probably he has something to say about the ESP32.
Yeah, it continues to be exciting to see all the things going on with it. It's funny, there was the chat going on with locals, and someone has posted to GitHub. They've actually found a bit of a bug with the locals implementation in ESP32 Forth. So I'm busily fixing that as we speak, because it's actually quite bad. There's a spot where it's not the length of the name of the local can actually cause a problem. So little fidgety things like that. One thing for folks that are following along in the repository, I finally got around to clarifying the license for ESP32 so it's under an Apache 2 license, and that's all sort of now done up nicely in the repository.
I would like to add to this explanation of license that there is a confusion. There was a guy in a group writing he wants to make OTA with ESP32 to deliver a software to his customers as closed software. This is a crime. This is a crime. I don't allow this to happen in our group. So I answered to this guy in the way it should be. Arduino is an open source platform. You can't use GCC compiler, and you can't use Arduino as closed source. You need to deliver your customer. Of course, you can make business. You can grow your company with that, as many people do in the world. This is a fantastic platform. But software should be kept free, because this is the way other people can help your customer. And the business grows. This is not, if you close your software in today's world, in the 80s or in the 90s, there was another system, there was another business opportunities. But today, delivering closed software using open source tools like GCC compiler, like Arduino, like ESP Wi-Fi stack, it's not allowed. This is not allowed, and it is a crime. This is not a joke. It's a crime. This guy can be processed, and he will pay a high sum. He will pay a lot of money. He will lose all what he did. So we must be careful what we write in the group, and with this license, we must be careful.
Well, almost all embedded systems today, you know, have a micro in there, and almost everybody's using GCC compiler, and you can't have access to the source code. So I don't know what to say about that. You know, if somebody wants to embed an ESP32 fourth board in a coffee maker, you know, the user doesn't get access to the source code.
No, it's obliged. It's obliged to your software should be open source.
I would like to clarify, the output of GCC does not have encumbrances, is my understanding, but the issue with Arduino specifically relates to the libraries that are included with Arduino. GCC itself is GNU licensed, but as a compiler, its outputs are widely distributed in a closed source form. There are some issues around some of the libraries that can be bound with it as well. My understanding is that ESP32 in general, if we were using the SDK, then we would have, there wouldn't be this GPL encumbrance. But
we use RTOS also. RTOS is open free software. Nobody can use RTOS and distribute a binary. This is a crime. It cannot be allowed this to happen.
Now, guys, the GCC compiler output is free, so as long as
Cornelius, you're breaking up super bad.
It's not bundled with the product, and either under proprietary closed. A minute to get into Wi-Fi range. Just a moment. That's better. Typically what happens. Okay, that typically is what happens if you are listening to a conference while you're in your backyard trimming dead wood from trees. Sorry about that. Anyway, the GCC compiler output, as mentioned, is free, so that's not a problem. Problem are the libraries. If you include a library which is under GPL, then you have to publish, then your source code is subject to the GPL and you need to provide source. If the libraries that you use, all of them, are either under some proprietary license that grants you the right to distribute them with the software without having to show source, or the library is under LGPL, then you have to include a copyright notice. You have to state which LGPL covered licenses you have to use or you are using. And should you change anything in the source code of the library, you have to provide changes. I went through this for multiple products at Alcatel, and I've been through this thing back and forth. So it depends. It really depends on what this commercially motivated person was intending to use and how. So without looking what he was really intending to do, it is in general very difficult to state that something is permitted, allowed, or partially prohibited. The legalese here.
It's simply to read the Arduino license. When people use Arduino, they need to read the license. When they use RTOS, they need to read the license, etc. and etc.
Yep. Yeah. In general, read the license and read them carefully.
JPL 2 and 3.
Excuse me, there is no Arduino license. Most Arduino boards are alike. All these ARM32 boards from ST and all other computer manufacturers, they don't have anything to do with Arduino. They just have the format to put plugins onto it. And maybe they do some special things. It's opposite. The original Arduino design was open source. This was allowed to make copies of it. In opposite, Raspberry is not open source. There's one chip you cannot copy. So there's no replacement. So
but Rolf, in the case of the ESP32, we started from Dr. Ting development over Arduino, and Brad continued over Arduino. And we are a hobby group. FORTH2020, we are more for makers and hobbyists. So if somebody needs professional advice from a lawyer, etc., he needs to go to the specific consultancy with lawyers. But as far as I understand, we distribute this for Arduino, the ESP32 Force.
So this brings up a big picture question. So we get somebody on the group, they start developing using the ESP32 Forth. Can they actually embed it inside of a product? I would
not
think
at the moment, not at the moment, Don, because so far as we're building with Arduino, the Arduino libraries are encumbered. Now, my understanding, again, not a lawyer, but my understanding of the ESP32 tool stack, the RTOS, the version of free RTOS they're using is under the MIT license, so that piece isn't an issue. The underlying tool chain doesn't produce an encumbrance, but specifically the Arduino libraries and that set of software, because that gets compiled in when you build the binary, then that's where we get the encumbrance.
Don, your question is very interesting. People should not be afraid of making a product with Arduino. You can, but you can write to Arduino because they have a commercial department, and you will pay to them a small license and you will be free to make everything with that. You can continue your production. It's only to say, this is my product, I want to be part, I want to use your Arduino, and you enter into the commercial sector of Arduino. They have a commercial sector. And what else? What we are defending here is the open source. So if you make a product and you put on GitHub your code, it's perfect. You make business, other people do business, everybody's happy. If you take free software, you take free software from Brad, free software from our FORTH2020 group, free software from Artos, free software from everywhere, from Arduino, and you sell the binaries closed, you're a criminal. This is the only problem. But if you continue in the open source and you do business, this is perfect. I say, marvelous, do it.
I think we probably should put something in there because someone someday will develop a product, and because there's no way we can prevent that. And I would think we would want to encourage it, to tell you the truth. But we should put maybe Brad, in your little license thing, put a sentence on how, if they wanted.
I should probably flag in the so. Again, I intentionally did Apache 2 with the ESP32 4th core because I figured that was a GPL compatible license and sort of did the least encumbrances, and I didn't want to make assumptions about what to drag in there. But at flagging this concern that if because the thing needs to currently be built on top of Arduino, then you'd have that issue. It is in principle possible. Remember how, Don, we built for the Solo using the ESP IDF tools. With those, in principle, you could build a flavor of it that wouldn't have that encumbrance. But again, I haven't exhaustively gone through all of the licenses there. And the issue is that right now we're not just using sort of Arduino ephemerally. We're using a bunch of different libraries. So you'd have to go through and pull those all out. Which could be done, but or pull out references to those rather.
Yes, we are using libraries for Wi-Fi, for sensors, for everything. It's a library. We are using library. For example, Demitri is using a library of a guy from Italy to make the VGA output. It's all open source. So nobody can today deliver OTA binaries in the Arduino world. This is
I'll
crazy.
stick a note basically, I'll try to put it somewhere prominent to encourage folks to really examine the licenses and sort of, because we don't want somebody sort of they may see the Apache 2 license and then think, oh, okay, I'm fine, and then forget that Arduino has these issues. So
I think it'd be a small price to pay to go register it with Arduino and then call it a day.
To be fair, I don't know that. So ESP32, the issue also is that it drags in. It's not just the Arduino folks. It drags in the ESP, the plugins for Arduino to support ESP32 from Espertif. Those also have some issues as well. So it's the whole stack there. We'd had to. And I'm not saying this is a useful goal, but if the goal was to unencumber the thing, what you would need to do is start building with the straight tool chain from Espertif. We'd have to remove all the references to anything Arduino, any of the Arduino libraries. So it wouldn't be a small matter. Certainly.
So I guess maybe just put a disclaimer down there that we use a lot of multiple open source libraries, and and just make that disclaimer. And if you're going to use this an embedded application, you got some work to do.
Don, you know why I am remarking this, because we had this guy. This was a fanatic or very aggressive guy in the group with the OTA. OTA is not for force. We use force is to send text to the chip. So in force we use text files. This is from day one. From day one we use we don't use binaries. We use text files. And this was my first comment to this guy, and he did not like it. He went aggressive with the group. He blocked you, and he made other problems, and he's doing problems out of the group. And these guys, they simply don't understand they are making a crime. They are making a crime. They don't know what they are speaking. This is the first problem I see in this new kind of contact with people over Facebook or etc. People talk a lot without knowing what's behind. They don't have experience. They are talking of binaries. This is complete madness. This is madness in the today world, to distribute software over OTA. This does not exist. You can do it for yourself. You can do OTA in your home, but you can't sell a binary and distribute over OTA. This is.
Well, an embedded system is not distributing a binary. It's a product, and I think what are you saying that if you sell a binary, a compiled binary, and you put a price tag on that?
Yes, Don. GPL requires you to GPL and GPL3 require you to not only sort of hand over the source code for the thing, but also potentially the patents.
You are using other people's work, Don. This is the thing here.
Oh yeah, I'm just trying to. The only reason I'm bringing this stuff up is to clarify it. I'm not making an argument against it one way or the other, but
no. I mean, imagine the same. Imagine this. You have here a lot of. Oh, I can show you. You have here a lot of people working, and you are the last one in the chain. You are here on top, and you take the money from all of them, and keep for you. This is not correct. You are making money out of the work of a lot of people. So you must be careful with that. You need to pay the work of other people. It's time. You need to pay that. And these companies, they have these special departments. Arduino has a commercial department. So it's only to enter in contact with the guys. They will explain you all the way, and you will continue making business, paying a small fee.
Although, to be honest, it would be the random Arduino libraries that are GPL'd I'd be more worried about. The Arduino folks, they have their set of stuff, but there's a bag of other things that we've started to pull in, and those would be harder to track down the authors, all of those things, if someone were to go down that route. Honestly, though, for ESP32, a lot of the core libraries are built on top of the calls into Espertif. There's Espertif equivalents, and for a variety of reasons, I've been wondering if calling directly into the Espertif APIs might be better, just because you're saving one extra call chain hop, and you're sort of working through an abstraction that was meant to emulate Arduino, which is sometimes good, but the ESP32 isn't an Arduino board either, so there's differences in but that's a separate issue.
Okay, guys, we have can someone see if Rick Carlino is in the group or he left again? Rick makes a farm robot. It's a very interesting machine, and he will in next meetings present to us this farm robot. It's very interesting. I propose, if you all agree, we make a 15-minute coffee break, and after that we have Brad Corner and Don Golding with the Triune system. It's okay?
Sounds good.
Okay, see you in 15 minutes back.
Pablo, how's it going?
Hi, Dimitri.
Hello. How are you doing?
Well, very well. You?
Oh, glad to hear. Yes, yes. Are you still working on the ESP32?
I'm still, because work is consuming all my time.
Oh, same. Me too. So busy. I wanted to be further with my FPGA work, but I'm only so far, so hopefully soon I can get further.
Very nice work.
Yes, yeah.
Here in my country is more difficult get this technology, and I am in software, not hardware.
I see. Yes, or the FPGAs. Yeah, I imagine. I've done some of both. In my work, I've verify hardware. I just write tests. So I'm not really a designer, but I know maybe enough for some basics.
No, very advanced. I see you work, and Ilya is very well professor and explain very clearly.
Yes,
very
yes.
Clear.
Dimitri, you are from USA?
I'm from the UK.
Ah, UK. Okay, I'm from Germany. But if you're not from US, the US like Verilog and the Europeans like VHDL. So
This is
UK
true.
just left the EU, European Union, but so the problem is how much effort was it for you to transfer? So you said you got to system Verilog instead of Verilog, so you just added comments or added constant instead of data. Come on, this is not efficient work. You might have added comments. Why didn't that? Isn't that done by the original author? But to change the script engine more or less, just to have this. Think of people who transfer software from Pascal to Modular 2 30 years ago, or now from C# to Java. Okay, this makes sense, or vice versa. But it's just, you have to do everything, and it's different syntax, and it's not everything the same. It's not one-to-one. You have to think about, you can make bugs. So you have to verify both the design again of the original script language, and then to be sure, you have to write so many tests that the new script language really does the same.
So are you talking about programming languages or hardware description languages?
It's the same. It's the same. So Verilog is not 100% compatible to system Verilog, I'm sure, and Verilog is not 100% compatible to VHDL. It's not the same.
That is true. Verilog and VHDL are definitely different. As I understand it, Verilog is just a subset of system Verilog. You can choose to use those features or not.
The problem is
my work, except for the J1, my work is not translating things from Verilog into system Verilog. I just used the J1 as an example to show how some changes can make things a bit more readable, but it was a one-to-one mapping, really.
Okay, you showed the screen and you showed a light version of the software. So was it efficient? What is enough to have the free license of the tool chain of the chip manufacturer, the Verilog chip so the chip manufacturers, so Xilinx and Intel or Altera and so on, they offer both because they know the people are different. But,
yes.
I did not know that the free tool chains now include system Verilog and not just Verilog.
Yes, yeah, they do. The thing is, really, VHDL. I would say, of course, VHDL and Verilog are completely different. I'm not suggesting they're the same, but the level of things you have to process in VHDL is comparable to system Verilog. In fact, the first time I saw behavioral code, it was written in VHDL. And I was amazed. I was like, wow, this is so different from what I did at university, because I was now looking at industry code, and they were just writing what the hardware needs to achieve and not any of the components or logic. And then when I was learning a system Verilog, because I use it for verification, but it can also be used for design. What I basically learned is that they try to make Verilog have some of the features that VHDL has. And so I chose to go with it just because it's more familiar to me than VHDL. But I could have done this in VHDL as well. I think they're about similar in features when it comes to hardware, but for verification, yeah, that is where System Verilog's strength really is.
Might you repeat the word with behavior? So I know behavior-driven development for programming. You said now with VHDL you can do what behavior?
Hold on, let me. I'll write in the thing. Behavioral. I spelled it wrong. Hold on, let me double check this.
I'm from Germany, so I learn the words by you. Then I can look up by Google, whatever.
Yeah.
And so I'm with VHDL,
Yes.
I'm rookie. I had a university course many years ago that was paradigm.
Behavioral paradigm. So you have, there's a few, or three, I think. Behavioral is one. The others are, Ilya listed them. It's like structure. The way I think of it is, I simplify it. Behavior is just what it does, but not how it does it. Then you have logic. People write logical expressions.
So is it different? So the vice versa is a traditional hardware description, and this is describes the logic. So behavioral is new, and what is the name for the old stuff? So the new is with something when something new, he also has always a name for the old stuff. Structural programming. Did the OO people call?
Yeah, true.
So what is the traditional name for the behavioral paradigm people? What is the traditional one? Logic. The logic describes they describe the traditional way is to describe the logic. So A plus B is ANDed to C.
Okay, yes.
What is the term? You're native English. So what is the term?
Let me check. I don't remember the official name for that. I use the term RTL in my talk, which is RTL, which is register transfer logic.
Register.
But
yeah, okay.
Sometimes I've seen the word RTL used to describe any HDL code, so it's probably too broad.
HDL means
hardware description language.
Yeah. Any traditional code.
I will also drop these in.
Demitri, could I ask you something?
Yeah, sure.
Thank you very much for the
yeah, no problem.
You mentioned that you might implement a garbage collector. Can you just give me an overview of what that would entail in hardware? It sounds terribly complicated for me.
Okay, so I mean, there's a number of different methods, and I have not researched all the methods yet that are used. But the basic principle is that, or one of the earlier methods is you would check all the pointers. And what you do is you dereference all the pointers to find all memory locations that are accessible.
But doesn't that mean you need an extra set of registers to point to those? So you need all memory addresses or accesses must be indirect through a register that looks up the actual address.
There could be elements of that. You do need to have a list of free addresses, and otherwise and then you can go through that. However, I have worked on designs that are of that nature. I don't think it followed a traditional garbage collector. I think it was more of a say when to deallocate things, but it wasn't a one-to-one mapping. It wasn't like, oh, deallocate this memory or that memory. It was more like signals were sent back to say which what the status of the operation was, and from that the module could deduce, okay, that means that this memory is no longer being used. So it's definitely possible, but it's not something I've personally implemented myself. I'd have to find probably someone else's work to do it. But on the level of algorithm, I have implemented it, and if you're interested, I could send it to you. I have a Forth garbage collection in Forth. It's just a very simple model, but it can help you understand the principles.
Yeah, excellent. I'd like that.
Okay, sure.
Now, the thing is with defragmentation of memory, you'd have to physically move stuff around if you didn't have that extra layer of index registers, right?
I see, because of where things are. It's just pointers, really. You have pointers, like when you have variable in Forth. Well, sorry, let me not use the word pointer. Let me use the word address. Use the word address. You get an address, and we're not really concerned where that is. We just know that it's a piece of memory that we're currently referring to. So I don't think this is too much of a concern. But what you do have to control is the list of addresses, or sorry, not addresses, which memory locations are free for allocation. That's really what you got to keep track of, and that can actually be done with a stack. You can actually use a stack for that, or just a simple list to keep hold of those.
Now, if you have a fixed record size, like say 32 bits, 4 bytes or something like that, it'd be pretty easy. But if you have variable width, that's more complicated. Did you implement the variable width, or is the fixed width?
Variable width of what? Sorry.
So it's a pointer to data. If the data is fixed width, let's just say it's 30. It's
I
4
see.
bytes.
Yeah.
Then it's really easy to have a like a free flag, on an address or something like that. Versus. Or you put it, or you have two lists. You have a free list and you have a used list. You can move the pointer from one list to the other. If the data structure is, the width is the same. So
I see.
With your list stuff, is the data width the same, or is it variable?
It was the same. And
that makes it easier.
Yes, the size of the memory that's allocated each time is the same. It's just enough for the two pointers, car and CUDA. Perhaps I can share the code. Actually, I'll just bring it up, unless we're going to start again shortly.
That'd be cool. Peter, how much time we got?
Well, we are back, but keep on the talk, no problem. Don't.
Typically, the challenge is that
these are good questions, not things I'm prepared for, but I'm glad.
Who is talking? I can't hear you. Somebody was saying.
Someone. Oh, is that you, Ken?
Yeah.
Hello.
Sorry, I've had to join on my mobile. My laptop wasn't working. Yeah, VHDL came out of the United States Defense Department, and it's got a syntax a bit like Ada, whereas Verilog, the syntax is more like C. So whilst they have similar functionality, they started off in completely different camps.
Yeah, I agree, and I've done a bit of Verilog, bit of VHDL, and in general, what I'd say is that Verilog is usually used for much lower level things, much lower level logic, even things like when you do synthesis and you get a net list, or all that logic is expressed in Verilog. Doesn't mean it cannot be done in VHDL as far as I know, but VHDL has more structures built in for higher level modeling, which probably explains why the first time
may well be the case. Yeah, I prefer Verilog only because I'm more familiar with the syntax of C. It's like you're standing at a crossroads and you decide which road to take. Really, you either go one path or you go the other. Maybe if there was a hardware description language based on Forth, that would be quite cool.
Yeah, I mean, I did have a plan at the very start of this project, an idea that the processor could be written in Forth, and then that Forth could be translated into a hardware description language, as long as the Forth that I used was a subset of all Forth features. So you can't do everything that you can do in Forth, like create does. How do you synthesize that? But there are probably some structures, as long as you follow it, it can be translated. However, I ditched that idea when Don came back with me with all these updates to the processor, and I said, this method it's nice conceptually, but it's slower. It's probably better just to write in the HDL, especially because it's so high level to begin with. But that translation, I think, can be carried out, and it's been done before by other maybe not Forth to Verilog, but Forth to logic device has been done by Testra, I think.
Right.
Paper on that.
There was one company that about 15 years ago was proposing a hardware description language based on Forth, but the website hasn't been updated for 15 years. So I'm sure somebody had that idea in the past.
Just tell the website if you know of this company.
I'll try and find it for you.
And write it in the chat if you like.
I came across it. I came across it recently, but it was almost a dead link.
Then look at archive.org. If you know the website, use archive.org, and there you can enter the website, and usually they have a copy.
Ken and Rolf, if you prefer, we continue with the two presentations we have from Brad and Don, and after that we do a Forth cafe, and we chat freely. What do you think?
Okay, that's fine by me, Peter. Thank you.
Thank you. Sorry for the interruption, Ken. Sorry, Rolf.
No problem.
Brad, we have a Brad corner now, and then after you, Don. If you want to say something about the new developments. You need to unmute, Brad.
Let's try that again. Yeah, so most of the items since last time have been sort of housekeeping items. And as I mentioned, there's that clarification of the license. Another one is that I've now changed things so that I'm maintaining the notion of a stable release. And so there's a branch for 7.05 that's a stable branch. And if you go look on GitHub, there's that's being sort of maintained separately. And I've structured the publication for the documentation here so that it keeps around that notion of the stable release, and I can push them out independently. I'm eager for feedback in terms of what things are appropriate to cherry pick to a stable release. So far, I've mainly focused on sort of things that are pure bug fixes that don't produce a lot of churn. The biggest delta right now between the 7.05 and 7.06 release is that the 7.06 switches the web server over to being implemented more heavily in Forth rather than relying on the Arduino web server library. The other thing as part of that process is that I've, let me shrink this so I can actually move it around. I'm also now maintaining a release archive. So if you want to be able to go back and get an old version, I've labeled them going forward with a sort of a fuller version number. And then there's also, within a given version, there's also particular revisions, and I occasionally push those out where it has the git hash of that particular push. Other things, there's some minor bug fixes. The recurse word was not implemented, and now is in place. Yeah, there's this. For those of you who are interested in locals, as I mentioned earlier, there's actually a rather sort of goofy set of bugs around locals that someone happily noticed. It seems that if you have a local with an 8-character name in the local, it does something wonky. So I'm in the midst of fixing that. Are there any questions about status of things and the new release process? I'm not quite sure when I'll promote sort of the beta to stable, but I welcome feedback on sort of the right way to approach that and so forth.
Brad, I have a question. So, as you know, I'm not a fan of RTOS's, and I want to use just one counter timer in the ESP32. Which one do you recommend I use?
So, as far as I can tell, if you're using no libraries actively, like if you're just using the bare system, then any of them is fine. So counter 0 is perfectly reasonable. There are hints that some of the libraries make assumptions about particular timers, but I haven't exhaustively, for the set of libraries that we're pulling in, sort of carefully teased out which counter they're using. It's sort of a bit of an allocation problem, I guess, in terms of if they all make particular assumptions about those counters. My guess would be if they're being cautious, they probably don't make any dangerous usage of them, and so then it simply doesn't matter. But I feel like I've hit a case where I did a combination of things with the counters or with the timers, sorry, the counters, and then ran into an issue. But I think 0 seems to work fine, and I tend to use that one.
So you wouldn't use 3. I mean, I would think most people start with 0 and work their way down. Yeah. You wouldn't use the last one because
I think it doesn't matter, Don. I think my guess is that anybody crafting an Arduino library is probably reasonably careful to not, if your library has this sort of weird dependency where it might clash with another library, you would probably have issues. So they probably all are very cautious. And a lot of the libraries aren't relying on counters directly. They're relying on, they're calling into the ESP's set of libraries, and most of those rely on, tend to rely on other signals to know when to trigger. I suspect it may just be that we don't have a rich enough set of things that we're pulling in. If we had a bunch of libraries that needed a time source, then there might be more of a problem. But I think most of the ones we've done so far, web server library isn't relying on a time source to do anything particularly. There's other signals it's using. Some of the libraries for the libraries for SPI and whatnot are relying on SPI signals. So I think it just happens to be that time doesn't end up being relevant. And I see there's a comment in the chat. That's not related. Okay.
Okay, I'll just use timer 0 until I blow something up.
Yeah, I think honestly it'd be more, if you were able to actually find a bad interaction, I'd be more interested to find that out, just because then we would know. Whereas currently, I think there's, we haven't exhaustively looked at all the libraries. But I think from what I've seen, we just don't have anything we're pulling in that happens to do background work that way. Quite possibly also because there's the option of using threads and other options as well. So they may just be relying on that. Speaking of the interrupts, I pushed out a fix last night. Actually, Peter was noticing, or had forwarded along rather, some discussion going on. There was actually a symbol collision due to case between the call to delete a counter to delete an interrupt and the constant name for setting an interrupt to disabled mode. They both happen to be ESP something something disabled.
Was not, sorry, Christian was not able. Hello?
Hello? I can hear you, Peter, but you're very faint.
Now?
Yeah. You're very soft. Oh, maybe it's just on my end.
Christian had a problem with the interrupts. He was not able he could not disable the interrupts. And Bob found on the vocabulary there were words 2 times defined. No, I sent you this by email.
Yes, so I've worked around it in the way that you suggested, and so now all of those constants for that particular call are prefixed with a number sign. It's an interesting problem that I believe both G-Forth and Win32Forth work around this by having the use of they have a notion of a vocabulary can be a table instead of a regular vocabulary, and in that case it becomes case sensitive. So that might. I mean, given that we're dealing with C libraries, case sensitivity ends up mattering more. So that might be a direction to explore. Or I mean, this is the first collision that we've had, or at least that we've noticed. So maybe may not be a thing. But curious if others have had experiences around this category of thing. You know, case sensitivity mattering in C, and so then you're interacting with a C library, and then you have 2 symbols that would have been different by case, but are the same in Forth. Let me try to find I can show the particular example here to motivate it. I'll just show the.
Christian, are you in the meeting?
So the particular symbols in this case.
Yes, I'm there.
This is for you. Brad resolved the problem of the interrupts.
Yeah, so it happens that there's a binding for there's a binding for let's see. Sorry, GPIO enter. So GPIO enter disable because Forth is case insensitive. This one collided with this one, which previously didn't have the number sign in front. So for now, taking Peter's great suggestion of sticking a number sign there, but longer term, we might want to think about maybe tables or some other way of enabling case sensitivity. But it's actually kind of an interesting, like, I'm curious for folks who know more of the long sort of arc of Forth history. I assume that the lack of case sensitivity was just a reflection of the era when you know there weren't encodings that distinguished case and a tendency for sort of tolerating both cases. But it's a sort of a strict, you know, most contemporary languages have gone the other direction, but I assume that's just a character set thing.
Remember that Forth was case sensitive originally. Polyforth is case sensitive.
I was not aware of this. This is in Chuck's original implementation, or was there?
Yes, Chuck's original was case sensitive.
Interesting. I was unaware of this.
The case insensitivity, I think, came with FIG.
Ah.
I think. Of course, I wasn't around in that time either. So,
Bill, is this something you recall the lineage on? Bill looks like he's maybe.
Bill went to sleep.
No.
He's meditating. He's meditating. He's not he never sleeps.
Sleep what?
Bill, we were wondering if you know the history of case sensitivity in Forth, and sort of how we landed in a place where it's a case insensitive language.
I wrote the history of case sensitivity. Do you have an hour or two? No.
Yeah. Yeah.
Well, and briefly, Chuck's originals were 3 letters, a number and 3 letters. And then in the FIG model, it's adjustable. So you set a constant, and when a word is compiled, it's compiled with the length and as many letters as you set in the constant. And then it's also set with a shift character, so that when you compile a word, if you have shift set, everything shifts to uppercase. If shift is not set, it's mixed case. So FIG Forth had variable length names and adjustable case selection.
Yes. Okay. I was correct. It was FIG.
And what was the sort of rationale for was this just a purely sort of size and encoding trade-off thing, or what was the motivation for not keeping case sensitive?
In general, broadest possible acceptance, because programmers at that time were saying, why are we stuck with 3-letter abbreviations? And yet I didn't want to go against the grain of all of the stuff that Forth Inc. had done. So this way you could accommodate both worlds. And when you look at it, like so much in Forth, the code to make this happen was maybe 40 bytes, 20 bytes, something like that. So it was essentially, it was cheap. The trick was making the variable length name in the header, and we'd have a bit, the 8th bit was set at the last letter of the header. So when it was scanned, you'd know how long it was. Now, as a side point on that, I got a call at 2 o'clock in the morning from John Draper, and he was yelling at me saying, Bill, there's a bug in your code. You got a bug in your code. And if you know John Draper, he could get pretty worked up. And it turned out he was using a word in his system called look, L-O-O-K, and he had it set to 3 letters, and it was conflicting with L-O-O-P. And so I had to guide him through the difference. And if he set to a full word length, he'd have no collision. Anyway, it was 2 or 3 in the morning.
Well, thanks for that background, Bill. So yeah, those were the items that for this time with ESP32 Forth. If there's other concerns and questions, or especially any feedback about the move to a stable branch or things of that sort, reach out now, or reach out and let me know, or if there's nothing now.
Atle is also using the ESP32 Forth. I don't know if he has something to ask the group or to you.
No, I was just wondering, will any of these libraries, like the OLED library and a couple of very much used libraries, be part of the standard the standard ESP32 Forth?
I'm open to it. I think at one point, am I remembering right, there was a poll. I confess I'm a bit of a Facebook novice, and so I remember there was a poll on folks proposing various libraries, and I confess I haven't prioritized putting that in. Maybe I go find back that poll and put them in, because yeah, the OLED one, for example, seems like a reasonable one to sort of standardize the way we embed it.
Yeah, that's on the wish list, and then there will be for this fourth mobile that Peter and I are working on. We have some requirements. We need a compass. We need the time of flight sensor, which has me still scratching my head, and the ultrasound would be nice to have there. So there are like 4 or 5 at least that would be very nice to have. So we don't have to recreate the whole thing every time a new version comes out.
In my opinion, we should have a version for the fourth mobile independent of the ESP32 that Brad is doing. But because what happens when you insert a lot of libraries in the kernel, you create a problem, you create a complication. Brad will not be able to add more stuff about.
I wonder if maybe we can we need to design for a little more modularity. I wonder if perhaps adding if I structured it so that there's an include of a secondary header, so that you could have additional bindings live in a separate file, so that when you pull in a new version of the INO file, you could sort of put the two alongside each other or something of that sort. That might
great. That'd be great.
Yeah, I'll put some thought into how to restructure that to make it, because I think that's the trouble, is you want to be able to have minimal to no changes to the INO when you bring in a new one, but be able to continue to have extra bindings.
We cannot add these libraries because they are huge. When you insert, like Atle is saying, when you insert all these libraries, laser, ultrasound, etc., it becomes a huge system. And you will not be able to develop force. We need a force and special versions, one for the fourth mobile, one for the other thing. These are different things. This is part of our programs, but not of the development of.
But I think I can make it easier by adding a sort of a hook, so that when you have a file sitting next to it, you could put all of the modifications in that file, rather than having to sort of mix them in the source code and then have
because what happens, for example, what I detected OLED. There are 2 libraries. One is from Adafruit, and the other is from another guy. And there are many versions. There are, I think, OLED are 4 different versions. And some are not compatible with sensors. Others are. Adafruit has a library that is compatible to their line of sensors. But if you use other sensors from China or other sensors, they are not compatible. They create. So if we include in a force special libraries, we will enter in problem. This must be outside of the development.
Yeah, the ideal thing would be to put all the rotten eggs in one basket, so that when you include a library, first you parse that library and create forth bindings for it to create those macros that we need from the library automatically.
Yeah, I think it's possible to sort of import a thing, but I think then the other challenge there is that we don't have a way to sort of script that. But I guess I could try to make a pre-processing tool that does something like that. I don't know. It's possibilities, but I think in terms of I like this idea of at least making it more practical for folks to have a clear place to inject things. I think that will at least make your immediate problem more palatable. But yeah, the idea of sort of automatically sorting through the headers, that could be done, but it could also be tricky and might fail in sort of subtle ways if done.
We don't want to create too much work for you.
It's a hard problem living in a CFI'd world for Forth, unfortunately.
But have as a long-term goal that new versions of ESP FORTH32 Forth can come out and our modifications can be included automatically somehow. I could try to make an awk script that could do something like that.
Well, I mean, we have quite a bit of pre-processing that goes into assembling the INO file initially, and that might be something to consider. Is if you're making modifications to the core system, the INO file that I published is not what I edit. What I edit is a set of separate files, and then there's a big make file and some scripts to combine it together. And but the idea was to publish the INO file because that makes it easier for someone to just load that up in Arduino.
I am not for adding a lot of things in a forth. I am for a forth should be compact and always work every time. And all you add above is your problem. It's the problem of who is implementing, because there are so many options. There are so many, for example, compass. You have 4 or 5 manufacturers. Each one is different. So
yeah, if we make it in the kitchen sink, it'll be a problem because there's just only so much space on the board. And you know, this isn't
I lost with the compass 1 week to make it work. 1 week, 5 days working with that. It's crazy, but libraries are not compatible. This is the problem. It seems easy, but it's not easy.
Peter,
Out
did
of
you write it in
curiosity, what
Forth?
was the challenge with that particular library? Was there something unusual about it, or?
Well,
with the compass, it's the chip. There are two types of chips, and they have the same name, and you have to figure out which is which. One is HMC5880, I think, and the other one is QMC, but it's labeled HMC. So
it was an American manufacturer. I don't remember if it was Harris or which one, and he went out of the business, and the Chinese took the development of these chips, and they made a chip that works, but it's not compatible to the other. And libraries are mixed up in GitHub, and they don't work. It's terribly complicated. Then the I2C is also not working with the Chinese chip and the other. And when you add OLED, it does not work also. So it's a mess. It's better not including this type of things of low quality software inside ESP32 We will go crazy.
yeah, absolutely. I will withdraw my request for standard libraries in the ESP32 Forth.
But I do like the idea of a hook, so that at least there's a clear way. If you're just using the INO file, and then I need to think. I don't know if there are standard easy ways to they might still require like a one-line change or something to enable include this header file, but at least it would, you know, be clear.
Yeah, and it has to be done in that production system that precedes the INO file, right?
I remember 2 years ago or so, there was a Usenet talk of Elizabeth from Forth Inc. And about her. It was told she proposed in the 1980s and 90s to develop without libraries. And this was old-fashioned. Now, if I see that there is a problem with ESP and libraries and licenses, then we have the problem that this makes Forth not going to be a winner language. Nobody has problems on, let's say, C or .NET or Java with licenses, or Lua. They have always MIT license. So if there is a language with embedded systems and you cannot create a product to make money, then it's not a technology worth to be considered. So every automotive embedded system, or in a washing machine or whatever, the wipes stuff, the software companies, they want to keep the intellectual property, and this is the only thing they have, else they are copied by, well, somebody else. And so if the language does not allow not to give away all the intellectual property, but this is because there are so many libraries, huh? And not just a self-written force system. That's why everybody wrote force by itself for the last 30 years or 40 years. Then we have a problem. Chuck sold in the 1970s their force, his force, on a system to others. They got commercial software. So he had many applications. He sold the applications. And he didn't sell the application so that the receiver, the buyer said, oh, we can use it everywhere. We just pay Chuck once or the company, and then we can make everything with it. They got their force system. And Chuck, the famous quotation, said, unfortunately, he did not understand Bill Gates make money with his MS-DOS operating system he bought from his buddy. And Chuck said, we might have made force an operating system. So like it is now force on the in the bootstraps of computers. So this, something like this. And then they would have a product. And then they must not depend on libraries. So if the ESP problem is that you depend on libraries where you cannot use it, if you get another board with ARM CPU from ST and some other chip manufacturers, you don't have a license problem. Besides, if they have a USB stick function, they say the USB ID you must buy by yourself. The one we give you is just for testing. As they say, you can use the software, you can compile it, and then you can sell it. And this is the only way for small companies to make any money. In general, if you are in the automotive industry, BMW, Volkswagen, etc., say, we want all the source code anyhow. Yes, but they don't spread it around. They just want to have it in case of problems, and that the original software manufacturer cannot react because he died or the company is deleted. So the library problem, this is the most important thing of this evening, of ESP, can make makes a project just for hobbyists. ESP is never considered to be serious by the automotive industry, by the washing machine and white machine, the household machine stuff and so on. Because it was proprietary, it is not guaranteed to be available because it's from China and not from US and European chip manufacturers. And now with the library problem. So I thought that ESP force is like any force anybody wrote in the last 40 years, built from scratch, and well, is there an option library? I can include it, but I must not. It boots by itself anyhow. So if you don't, so the force system is totally wrong designed. If it says, yes, for Wi-Fi we need a library with a special license. Yes, but then the force system must say, okay, I load with and without this library. And this C library is just loaded by demand. And if this is so, then the force application is binary, has no problem with licenses. It can be sold. And just the license, the import of the library is done at the runtime. This is like Linux applications are sold.
But Rolf, the problem is that we're not running on a full system. There is no shared library to load at runtime. This is everything gets flashed onto this board, you know, when you flash it. And so
yeah, then you might do different flashing, two flashes. So the manufacturer of a thing might have a different flash, an external flash, and the problem is not the flashing, so that it is compiled to one thing. And everybody who wants to make money with Linux or Linux, as you say, says yes, but we just call the libraries in a way by calling external small programs like it is Linux style, and then we don't have a license problem because nobody is willing to put.
Everybody in the group needs to understand that in the moment, Brad is developing this alone. And we are supporting him as much as we can, promoting it, writing some libraries. What I am doing is not writing the libraries, but I'm writing the glue code or the macros. I am testing, other people are testing, like Christian. Christian is with this switch. I hope he resolves the switch fast and goes to new developments with this display or ultrasound. There is so much interesting to test. Don is doing this robot, this Whisker robot who created. Don was our inspiration. In fact, we are following what Don is doing, no? And all of us, we have limited time, so we cannot develop like companies like Forth Inc. or like Charles or like other people. We do this for hobby. And Brad, imagine, he works for this large company, so he has limited time. He has his family, etc. And we need to try to find the shortest path to develop, not enter into very complicated.
But the opposite. The Eclipse IDE 20 years ago, when they changed from version 2 to 3, they had a new plug-in system, which was, by the way, granted that they got a license to use it. And now Visual Studio Code, a new development, it's IDE, they have also a plug-in system. And all this means that all the plugins you can put inside, they must not be, they are not linked to the code. So anybody can write a Visual Studio plugin or an Eclipse plugin by some rules, but it is not linked to the code. So especially the license is not linked to the code. So you should think about a loader mechanism so that the libraries are just available with a symbol names, whatever, by something that you can say. So let's in other language they call it include by script language.
Yes. This is the idea of Brad. This is what we were discussing. This is perfect. This is.
I think he's proposing something at runtime. So because there is this notion of severability, right? If you can make a substitution, you can circumvent licenses.
It's not the problem that it's on the same flash. This is not the problem. The problem is that it is loaded not at runtime. And the loaded at runtime is exactly the professional way. By Eclipse 30 years ago, Visual Studio, whatever. So, all this plug-in hell, the DLL hell of Microsoft, is exactly the package hell of the other languages. So the packages have different status, different version numbers. They don't compile with the new C compiler.
Okay.
Whatever. Okay.
Fantastic. We have the top of Don Golding with the Triune system. If you like to present, Don, we are ready.
Okay, yeah, I'm ready. So the first thing I want to talk about is Christian's problem with the interrupts, because I've had a lot of experience in this. You do not, and it was someone, I would give you the credit if I could remember your name, but somebody in the post said something very clear and to the point. You don't ever have an intermittent kind of signal or a noisy signal running an interrupt. That's absolutely, you do not do that in an embedded system. Now, from a hardware solution, if you use a resistor in the cap, basically what you're doing is you're smoothing the data as the pin is mostly high, but it's going low a few times, right? So the average with an RC time constant, it's basically averaging it together, and it comes up at a slower rate, and then it flips the pin on the processor. So one of the critical things you got to do with embedded systems is you need to do multiple things at the same time. Well, what happens if you can't afford to put a RTOS on the chip? right? Well, what if you're using a 50-cent chip that has 2K of memory and maybe 10K of flash, for example? So the way that I've always done it, the way I started doing it with Whiskers, is I have one counter timer that is running at, let's just say it's a kilohertz, okay, 1,000 times a second. So you have what's called an interrupt service routine. So every 1,000th of a second, that fourth word, that function is called, and you can have many fourth words. You can have many different things happening in this ISR in the background. And when the ISR terminates, then control goes back to the main loop, okay, which is your basically the code that's running. I call it the goal level, but it's basically, let's talk about it in C language. So you have a main loop, and you have this because I use this in C coding as well. I have to do C coding at work, and I just simply make this ISR, and I got the C code that's running in this loop, and then this ISR is interrupting the C code at 1,000 times a second, and it's processing things. So what you simply do is you, in your ISR, you create a counter, okay? So it counts up to 10. Every time, 1,000 times a second, it goes out to the pin that you put your switch on, and every time that pin is high, you increment the counter. When it's low, you reset the counter, or you reset the counter. If it's high, you increment it. So let's just say that you have a bounce. So that's going to give you 1 millisecond is 1 kilohertz. So that means that you're going to wait basically 10 milliseconds. You're going to be reading this switch, and maybe it only counts 7 times, okay, because there was 3 bounces in the switch. Well, then what you do is you say, if it's greater than 6, that's a real switch hit, okay? And then you create a shared variable. You just create a variable, and it's just a flag, and that flag is set every time the switch is activated. And then maybe the next time that you come into the ISR, it will reset the flag, for example, or you let the main loop reset the flag. The main loop, that's probably the better way to do it. So it's more like it's called a semaphore in multitasking. So Christian, that's the way that you really solve it reliably in your code. Do not use interrupts extremely sparingly. If you can get away from using an interrupt and go with polling, it's a much better way. The only time I use interrupts is, for example, a serial port. That has to be on an interrupt, right? That's where you're talking to Forth over the serial port. So that has to be on an interrupt. If I was reading a compass, okay, I got an SPI compass sitting out there. I will poll it in the interrupt service routine. So I'll say that maybe I want to update the compass once a second. So I have a counter that counts, up to 1,000, because I'm doing this 1,000 times a second. So I have a counter that would overflow, once a second, and it would be high, and then high for half. Actually, you would do it a half second. So it's high for half and low for half. So if you wanted to update the compass once a second, then you say, oh, okay, the counter's at 500. I'm going to go ahead and I'm going to go pull the compass. So I pull the compass and I update the variable that's in memory with the data. And now what happens is your high level, your outer main loop, can go access that variable at any time. It's almost like it's reading the compass, but it's not. The ISR reads the compass, and the main loop just goes and reads the variable. This is a way to do real-time systems, and it's the way that I designed the Triune OS. And it makes it so simple. After I did this with Whiskers, and this is early, this is like 1990. Every single embedded system I've ever done always has a counter timer interrupt and an ISR, every single one.
Don, for example, in Whiskers, you have 2 switches.
I do the same thing.
Well, these switches, they don't go to an interrupt line in the microprocessor.
Nope, they do not.
If you need to make something like that, you will add a filter.
No.
A hardware
nope.
filter.
Nope. Nope.
A
I do exactly.
A switch directly to a microprocessor line is not good.
Nope. It works fine because you're doing it in software. You're doing it in software. So you're doing it in the ISR. And if you want to debounce it,
you get all the noise in the switch.
The noise doesn't matter.
From the chassis.
The noise does not matter at all. Doesn't matter. If it switches 1 time or 5 times, it doesn't matter. Because the first time in Whiskers, I don't care about debouncing it. If that whisker touches the post and changes the IO line, for example, I got a hit. You know, it's never.
But you don't use interrupts on this line. This is
I
what
do
I'm
not.
talking.
I do not.
This is what I'm talking. This is a simple input line.
No, the ISR it goes in and reads the whisker ports and will set these variables in memory when they're activated. Now, so does everyone know what a semaphore is in multitasking? So a semaphore is you have a variable in memory and you have 2 processes that are running at the same time. So one process sets the memory flag to true, that the data in another memory variable is valid. And then the second process goes and sets that flag to 0 after it reads it. And now the first process knows that the second process got the valid data. This is called a semaphore in multitasking. So when you're doing this, when you're using an ISR as a background task, and you create these variables that the goal level is going to read, your main loop, it's the same paradigm, it's the same algorithm as a semaphore. There's no, it gets rid of all the asynchronous timing things. What happens if a whisker gets hit at 1 second, and then half a second later, the second whisker gets hit, right? If you had to read that in your main loop, you would probably miss it, or you would, you can get all different combinations. But because my ISR reads it in a very periodic way and updates the variable where the main loop can read it at its leisure, there's no timing. The main loop does not have to be timed to this asynchronous data that's coming in on the robot. The biggest problem with designing any robot is the fact that you have all these sensors just pouring in information at completely disorganized timing. It's completely random. You could get a whisker hit and a left sensor hit at the same time. If you put all that stuff on interrupts, the robot would go nuts. So this is why everything is in the ISR. Now I call the ISR in my 3-level architecture, I call it the instinct level. Okay, so all of the sensors, reading the optical sensors, reading the whiskers, reading the motor current, because I use the motor current as also a sensor. It makes the whole robot a sensor, a whole chassis is a sensor by reading the current. All that's done in the ISR. And I keep the ISR super simple. I tried not to do very, very little processing. In other words, do very minimal processing in the ISR, just the bare minimum. Do your processing in the goal level where time doesn't matter. So this way you create a robot that gets all of this data asynchronously, simultaneously, randomly, and you don't have interrupts stepping on each other. And that's the biggest problem to embedded systems, when the engineer uses too many interrupts for too much IO. You get you could blow up the stack and the CPU, because every time you get an interrupt, it's got to push the stack. All kinds of nasty things happen, and you can get.
Is it safe to say you've effectively, you've implemented your own like real-time operating system effectively, by polling the sensors instead of allowing interrupts?
Yeah, that's absolutely true. So it's called a preemptive multitasking. And now, if you look at an RTOS is time slice multitasking. So each task is, let's just say that let's go with the 1 kilohertz example again. And let's say you allow 10 different tasks. So at 1 kilohertz, that's, at 1 millisecond rate, if you have 10 tasks, 10 into 1,000 is 100. So each task gets 100 milliseconds. Task 1 gets 100, then task 2, then task 3, and task 4. That's what RTOSs do. Now, here's the problem. What if task 1 was reading the whiskers and task 2 was, let's say task 1 is reading the left whisker and task 2 is reading the right whisker. Now they're asynchronous. They don't seem to be working at the same time.
Would you say, I think when the lunar module was, Apollo 11 was landing on the moon, I think they had the local radar on, which they never had on before, and it was generating so many interrupts. That was the abort that they got. So I think you're saying in your methodology, by not using interrupts, you would just periodically be polling that radar, as opposed to the radar saying, hey, I got a lot of data, I got a lot of data, I got a lot of data. And meanwhile, your OS is just busy servicing interrupts for that one. Effectively, like in your example, if one whisker was generating 1 million interrupts a second, your robot would just be fixated on it. Now you only allow it to, you're only reading it like 1,000 times a second. So you're kind of like ignoring those extra interrupts that it kind of wants to generate, possibly.
This is a fantastic example. So let's engineer that system using the way that I would do it with a counter timer and an ISR. So I would say, okay, this radar that I have, I need, for my system to work, I need to know as a resolution of this radar, I need to know 10 times a second what that data is. So instead of putting it on its own dedicated interrupt, I will poll it 10 times a second. I'll create a counter just for that radar in a counter in the ISR, and every 10 times a second, it'll go and poll the radar for its data. And then I store that in a variable that then the goal level, or that outer main loop, can read that variable at its leisure, and it says, oh shit, I'm getting too close and I need to react to that. Yeah, so you're 100% right. I've been using this technique. I just been doing embedded systems all my life, and it's very deterministic. It's simple. It's usually a few lines, even in C, it's a few lines of code to be able to use a counter. And it just works really well. It's very robust. So basically what happens is the instinct level, which is where the ISR is, that's that's a preemptive multitasker, right? So it's preemptively at a very periodic rate interrupting that goal level processing and going and accessing all of this asynchronous data that's coming in randomly into the machine, and it grabs all the data and it grabs the data and it shoves it up into all of their different variables. And then when the ISR terminates, then the outer loop starts processing again. And which is typically a loop, like a case statement. You know, if you got this problem, you know, you check the radar, you check the you manage your thrusters in a spaceship, you do all these different things, and your main loop is a loop, right? So that means that all that data is clean, it's updated, ready for that main goal loop to come around and process it in a very organized manner. So that's preemptive multitasking. So basically the instinct level is a background task. You think of it just running in the background as far as you're concerned. It's running so fast to the goal level, it looks like it's real time, because the goal level doesn't need this data more than, say, 10 times a second or 100 times a second, depending on what you're doing. And to your goal level software, it seems like it's in real time. So let's talk about an LED. Okay, I want to flash an LED, right? So if I put that in the outer, in the goal level, your foreground task, right? Your main loop, it stops all processing, because your main loop, you would create a delay of let's say you want to pulse it at a second. So you have a half second off and a half second on. Your main loop can't process anything else. It's sitting there waiting, right? Because you created this delay word. Well, the way you do it with having an ISR, you put the counter down in the ISR, and then you create a variable, right? That your main loop can read, and that variable will be high or low on this 1 Hertz rate. And when your main loop comes by and checks that variable and says, is it time to turn the LED on, and it's a 0, it just moves on and it processes the next task. So this is a way to build real-time systems. Now, the middle level, which I call the behavior task list level, it is actually called from the ISR. It's called from that instinct level. It's called from the ISR. So the last thing I do in the ISR is I have another counter timer that says, let's just say that the instinct level is running at 1 kilohertz, which is 1 millisecond rate. And I want behaviors to run at about a 10 Hertz rate. So I create a counter in the ISR, and the counter, and here again, each counter is a shared variable. It's just a variable in memory. And when it counts to 10, it will actually call the CFA, right, of the behavior processor. And see what happens with that is your goal level or your outer main loop is in pause mode, right? The ISR calls the behavior list, and now, so between the behaviors and the outer level, that's cooperative multitasking. It means they both can't run at the same time. So then it goes through that list and it executes every single thing in the list like a case statement. And when it terminates, then control goes back to the main goal or the main loop again, and it starts processing again. So the goal level and the behavior task list is cooperative multitasking, but the instinct level, which is created with an ISR, is always running, no matter if the goal level or the main loop is running or the behavior loop is running. It's still automatic. It will interrupt if a behavior's in the middle of processing and the ISR triggers, that behavior stops for a split, a fraction of a second, a 1,000th of a second, and the ISR gets updated. So it's a 3-level operating system that works really well with embedded systems. I've been using it ever since like Chuck says, he discovered FORTH. I discovered this way of doing multitasking in 1992. And it just really works for any embedded system. It's great for robotics because all of the data is so asynchronous and it's hitting the robot all the time. And there's, if you put it all on interrupts, the machine would go absolutely crazy. You would have, the machine would be, get locked up a lot, from interrupt stacking on top of interrupts and everything else. So use one single interrupt to create an intelligent machine this way. So that was a very good talk going into, let's see, where's my share screen? Where's that thing? Share, there it is. Okay.
While you're looking, Don, I'll say thank you for the answer.
Kind of long-winded.
But I enjoyed the answer, and I think I got some solution that will work. It all started when I tried to make a rotary encoder based on switches that was using an interrupt base in C. And I couldn't get the damn thing working with FORTH and interrupts. So now you gave me solution. Thanks.
Yeah, so what you can do is you have to run the ISR faster than your top speed of your encoders, right? So if your encoders, let's just say that you're running at the top speed of your robot is 1 foot per second, whatever.
I don't worry about speed. It's the cheap Arduino rotary encoder that looks like a pot. You only rotate it by hand to increment or decrement a value that you use for control of volumes or treble or bass, if you have some application to control audio.
Right. So what you have is you have your ISR read that at a faster rate than the resolution that you need. And then you don't have to use interrupts at all.
Okay.